Okay, well, thanks everybody. I'm very glad that you're able to come to this workshop. I'm glad to see there was so much interest here. My name is Brian Skinner. I'm at Ohio State. My co-organizer Sergey Frolov from University of Pittsburgh. I want to thank you guys all for coming. The point of this workshop is really just to consider in an open and unbiased and honest way as we can the question in the title, whether condensed matter physics needs to be worried about a replication crisis. Our first talk by Simine Vazire will consider carefully, will introduce us all to the replication crisis. I told her to be prepared for us all to be pretty ignorant about what a replication crisis is and how it happens. So she's going to introduce us to the concept of replication crisis and how it's been happening in psychology and maybe other fields as well. And then we're going to consider whether similar factors are at work for us. So I don't want to take time away from the speakers. We have three speakers lined up. Simine Vazire will go first. And I think just because this audience is so big and the time is so short, I'm going to ask you to not ask questions during the talk, to save them for the question period after the talk is ended. Finally, let me remind you that in addition to the talks that are happening live right now, there are some pre-recorded talks that are already hosted on the website. And I encourage you to go look at them. They all relate to issues involving reproducibility or non-reproducibility in condensed matter and related fields. Everything will be recorded and posted on YouTube afterward. So just in case you have to miss part of it, you'll get to see it later. Okay, Simine, why don't you start us off? Thank you very much.
Great, thanks so much for having me. So I'm excited to be here, and I'll admit, of course, that I don't know the answer to the question of whether condensed matter physics has a replication crisis. And I am going to be drawing a lot on psychology in my talk as kind of a case study or an example of a field where we did turn out to have quite a big problem when we looked. And I'll try to answer the question of, how would a field go about assessing itself and if it's worried that it might have a replication crisis. So I want to start with, I'm sure you've all heard of this idea that there are concerns about replication in psychology. It's been covered quite a bit by the media. And I want to point out one thing, which is that was alluded to by Brian, that it's not just psychology, that there's evidence in economics and other social sciences, and also very importantly in the biomedical sciences. In some ways, the crisis in the biomedical sciences has been known about for longer and going on for longer. And I want to kind of boil down the problem. It's not just about replication, and we'll talk about the difference between replication and reproducibility and so on in a bit, but really fundamentally to me, it's a problem of misrepresentation of the literature just not being what it seems. So if we oversimplify and we talk about, the results of empirical studies should look quite messy. They shouldn't always be perfect, but what we end up with in the literature is something where everything looks like it works, everything looks much better than it really should. And so given the time, I'm going to, go through this relatively quickly of how we go from having results that should look like the first picture, but end up with a literature that looks like the second, and how we managed to do that in psychology without even realizing the extent to which we were doing it and what some of the causes of that are. So first, some evidence that the published literature does look unbelievable. This is just a very quick and dirty summary of the proportion of results in different fields that are positive results. So in the case of psychology, that would be statistically significant results, p less than 0.05, but it could mean different things. Like you found evidence supporting the research hypothesis, not null results, not negative results. And so you can see that this varies across disciplines and that psychology is at the very bottom. So there's some reason to think that things are worse in psychology. And I'll be the first to admit that I doubt there are many fields that are quite as bad as we found ourselves in psychology. But I think the point, lest it sounds like I'm throwing my field under the bus, I do think that there are reasons to worry across many, many fields. Many of the risk factors and the problems that we turned up in psychology, we didn't know were there before, and we were pretty confident, we would have confidently said weren't there. And I think that's true in many other fields that without looking, you would have no reason to think you have a problem. But B, many of the risk factors are there. So even though psychology is the worst in terms of having over 90%, many estimates suggest 95% of our published findings are positive results, it's still quite high across many, many fields. And I would suspect that many people have anecdotes about difficulties publishing negative results or results that are inconsistent with the established literature and so on. Possibly for good reason in some cases, but I think that the barriers to publishing those kinds of results are too high, and it leads to a literature that just doesn't reflect reality, and that when we go and test it and see if things are replicable and reproducible, we're likely to be disappointed. So How did we achieve this in psychology? And I think the nuts and bolts of this probably look different in different fields, so I won't go into a great amount of detail, but it's not that hard. Looking back on it, it is a little bit embarrassing that we didn't realize the extent of the problems, because we were often training our PhD students, teaching these practices, not so much, not the textbook practices that we teach undergraduates, but, we would train our students to explore their data and then to rewrite the paper around the most exciting result and frame it as if that had been the point all along. So now that's a practice that we called harking, or hypothesizing after the results are known. So maybe you aim for a particular target, you had a particular research hypothesis in mind, you missed that, but what you do hit is interesting, so you move the target and say that that was what you were studying all along. And that might seem like a minor detail. We rewrite the intro, we write a different intro than we would have otherwise, but it certainly makes us look like better shots than we are. And it leads to shock and disappointment when things don't replicate, don't hold up, because we had framed it as if this was theoretically driven, as if this was planned. We had, statistical error control in place if we planned it, and so on. When that's not the case, the results are much less likely to hold up. So that's one of the ways, harking, but there are many others. So you might have heard of things like p-hacking, which again, I won't go into too much detail because I suspect that looks different in different fields. In our field, p-hacking means rerunning analyses in order to get the p-value below 0.05, because that is the criterion for positive result and publishability in our field. And we don't necessarily know that we're doing this. It's not super obvious. And it might sound crazy that as behavioral scientists, we were unaware that our behaviors might have been motivated by things like confirmation bias. But very often the kinds of things we did in p-hacking are very justifiable from a theoretical and methodological perspective. So you get a wonky result you didn't expect, you go back and look at the data, you see some outliers, or you see that something was miscoded, and so on. In some of those cases, of course, you should rerun the analysis. And then it becomes a gray area from the, of course, you should rerun the analysis cases to the, okay, now you're just overfitting, like plainly overfitting. And it's very easy to slide down that slope. So all of those kind of reanalyses with different specifications in order, not necessarily consciously in order to get the result you want, but you stop when you get the result you want. And you publish that one and you don't report the other ones. That's what we mean by p-hacking. And then other ways to make the literature look better than it is are things like file drawing. So this is when the researcher, if you can't p-hack it into significance, or you have more integrity than that, you might just not report the studies that didn't work. You convince yourself that, oh yeah, that experimenter is incompetent, I'm not going to report that study, I'm going to report the other studies that did work. And then publication bias is when that bias, that kind of sweeping under the rug of the studies that didn't work, comes from the journals, or the reviewers and editors tell you to drop that study because it makes the paper less neat and tidy, and so on. So these biases, we're kind of all in on it, and we all give ourselves good reasons why it's okay to misrepresent, and we don't think we're misrepresenting, but it's okay to show only the best results because we think those are the real ones. So why bore people with the experiments that didn't work, or with the analyses that don't show the effect? A couple of years ago, there was some journalism about this in Wired. They were talking about p-hacking, and they interviewed one of the authors who coined the term p-hacking, Joe Simmons, and he really emphasized how this is not something you go in thinking, I'm going to p-hack now, I'm going to make my results look better than they really are. It's something that happens very naturally and not without bad intentions. And so he says, p-hacking isn't necessarily nefarious behavior, but rather a human one, and one that the authors who came up with this term have been guilty of, and I have been guilty of many times over as well. They say at its core, p-hacking is really about confirmation bias, the human tendency to seek and preferentially find evidence that confirms what we'd like to believe, while turning a blind eye to things that might contradict our preferred truths. It sounds like some kind of immoral behavior, and that's not helpful. People don't understand the inevitability of p-hacking in the absence of safeguards against it. They think p-hacking is something that evil people do, and since we're not evil, we don't have to worry about it. But Simmons says that p-hacking is a human default. It's something that every single person will do, that I continue to do when I don't take safeguards against it, like pre-registering my studies. Without safeguards in place, it's almost impossible to avoid. And this has been my experience too, even since becoming fully aware and appreciating its bias on my results is very, very hard to avoid. And I have to not trust myself. Like the first step, right? And Feynman is one of the people who said this, I'm sure you're all aware, that the first step is to not fool yourself and to fully come to terms with how susceptible we are to these biases. And when we looked for safeguards in psychology, we realized that we don't have them. And if anything, we exacerbate these tendencies. So there's this problem where researchers are susceptible to confirmation bias. They already believe their theory. They believe the results that confirm their theory more than the results that don't. So if they get results that don't confirm their theory, they're going to scrutinize them more. And journals select the prettiest results. They want the exciting things. They want the positive results and so on. And so bad research practices are rewarded without anybody necessarily having bad intentions. And this leads to, as we call it, a vicious cycle. But I think it's really important to point out that nobody needs to have bad intentions here. Everybody can fully believe themselves, the authors and the editors and reviewers, to be committed to the truth. And one of the simple fact that we have 90+% significant or positive results in our literature is one of the pieces of evidence that things have gotten quite out of control. But now we have more meta-scientific evidence since this crisis has come to light. We've done more and better meta-science looking at how bad the problem is. And one piece of evidence comes from a new kind of literature, which is called registered reports, where authors submit their paper before they collect the data, and the editors and reviewers review the research plan, the analysis plan, and everything. And if they deem the study to be a high quality study that's important to run and important to know the results of, the authors get an in principle acceptance from the journal before collecting the data, knowing the results. But everybody is committed to publishing the paper regardless of the results. So this closes many of the doors to p-hacking, to harking, to selective publication bias. And so we can compare that literature where there's a lot less room for bias to the traditional literature, where we know that 90 to 95% of results are positive or significant. So this is an analysis across several disciplines that have registered reports. So first, looking at traditional literature, not registered reports, but regular papers, we already know something like 80 to 95% of articles find positive results, very few are negative results. But in the registered report literature, so among these select papers, and there's not very many of them here, and this, at the point that this analysis was done, I think there were around 100. For novel studies, only 45% find positive results, and in full 55% find negative results. And among just studies that are replications of earlier studies, and here by replication, I mean new data collection, but trying to follow the same methods and procedures as the original, only about a third find significant results, and 2/3 do not find evidence for the research hypothesis. So this is some indication of how bad the problem is, that when we kind of plug the holes and close the doors to many of these biases, we get quite different results. Now, there are other possible explanations for this, but I think that a very viable explanation is that many of those positive and significant results in the literature are not true positives. So what happened in psychology? Let me talk a little bit more about the specifics of what happened in psychology and how I think we got there, and the lessons we've learned that I think might apply to other fields. So first, as I mentioned, we have pretty good evidence now from meta-scientific research suggesting that the problem is quite big. There's this evidence I just showed you from registered reports, which is remarkably consistent with the results of replication attempts in psychology. So there have been a number now, dozens and dozens of attempts to replicate, sometimes dozens or hundreds of findings in psychology. And over again, they keep finding that a relatively small fraction of results can be replicated. And here again, I mean collecting new data, seeing if we get consistent results. So across the studies I've been able to find where I think the standards are relatively high for the replications, about 45% of articles that are submitted to a replication attempt are successful, which is quite similar to the proportion of positive results in the much more controlled registered reports. So something like half of our results disappear when we put in more constraints and put in safeguards to see if those discoveries are true discoveries. We also have a reproducibility problem. This is, by reproducibility here, I mean trying to obtain the original data from the original study and reanalyze it and see if we get consistent results. So my colleague Tom Hardwick has done some research, for example, here, just trying to reanalyze data from one journal, 35 articles in one journal. And this is a journal that requires the authors to share their data in code. So already these are relatively high standards, and authors who are choosing to publish in a journal where for psychology, it's pretty rare to require data in code. So they have reason to be more careful with their code, to be more careful that their results are reproducible. And even here, Tom Hardwick and his colleagues had a hard time reproducing the results for many of the articles that they attempted to reproduce. But it's really not even just a replication and reproducibility crisis. The more worrying thing for me is not that these results looked bad when we looked, it's how long it took us to look and for how long we were happy to just be confident that all these positive, too good to be true results were true. We put them in our textbooks. We put out press releases about them. And we kind of gave awards and built our credibility as a field around things that we should have been more suspicious of. And when I look back on how we let things get that bad, I think it's a few different things. One is just not having a culture of transparency. It was not the norm in our field for authors to be expected to post their data, their code, or even to post enough details about their method for someone else to independently replicate the study from scratch, which is quite shocking if you think about it. But we used excuses like page limits and boring and blah, blah, blah. And any competent researcher should be able to figure it out from the method section and so on. So it's quite embarrassing that we didn't even ask. But worse than that, I would say, is that we didn't think that asking was important, and we thought it was rude. We thought it would be impolite to ask another researcher for their data, that we, in psychology and in science, we trust each other, that science is based on a foundation of trust. And if we can't trust each other, then what do we have? And so on. But of course, that benefit of the doubt and that charity was extended more to some people than others. And what that meant in reality, if it was impolite to ask for data or impolite to question someone's results, was that the high status people got away with a lot, and anyone who wanted to come along and question that, tried to build on it and couldn't, that was only whispered about at conferences. And I kind of knew that that's how the world works. I wasn't that naive, but when I became editor-in-chief of a journal, I was shocked at just how openly that was discussed, this status bias. So after 1 year of being editor-in-chief, the publication committee who had hired me and who could fire me came to me and said that they were getting some grumbles from important people, that I was stepping on important people's toes. And when I asked for more evidence of my bad editorial practices, they forwarded me an email from a well-respected, famous person in my field. They didn't tell me who, but a senior, highly respected, award-winning social psychologist. And the email said, about a month ago, I had an experience with Simine that I found extremely distasteful, and I won't submit to this journal again. And I asked, okay, but extremely distasteful is not exactly a scientific claim. Can we talk about the paper and my decision and what was wrong and so on? And I shouldn't have been as shocked as I was, but it really did come down a lot to, well, you're pissing off important people, so you must be doing something wrong. And I think it comes back to this not valuing transparency and not valuing criticism and critique, and making it okay to ask, is this finding true or not, or is it robust or not, et cetera, and having this culture of just giving the benefit of the doubt. And when we went and looked, yes, things did look quite bad. So we found a lot of unforced errors in statistical reporting, lots of other things like that it made me realize, like, actually what we were doing in peer review at our prestigious journals was not picking the papers that are the most accurate, most robust, and so on. It was based on something else, because we didn't have a culture of poking and prodding and making sure that everything was there. And so those are the kinds of things that lead to a literature that's too good to be true, where things don't look as they should. And yes, while it became called the replication crisis and so on, I think it really was much more fundamental than that. It was a credibility crisis based on a lack of transparency and a lack of culture of criticism, which I'll come back to in a minute. So one thing that was interesting to me in the aftermath of kind of discovering the problems, and I would say we're still in this crisis, so I'm not going to say the aftermath of the crisis, but it's now become well established in psychology that there are these problems, or at least these phenomena of lack of replicability and reproducibility and transparency need to be explained. Not everybody agrees they're a problem. And one kind of spin on it, one approach to dealing with this problem is one I observed when I was on a National Academy of Sciences study committee on reproducibility and replicability. And I won't speak much about what happened during the process because that's confidential, but I can say that when the report came out, there was a chapter in that report on what should the public expect of science, how much error is normal in science, and so on. And in the end, I decided not to be a co-author of the report, partly because of my disappointment in how that chapter dealt with these questions of errors in science. So here's a quote from that chapter. I'm having trouble moving slides. So in that chapter, they write, the advent of new scientific knowledge that displaces or reframes previous knowledge should not be interpreted as weakness in science. And I agree with that. It sounds really nice, and most of the time it's true. But what this chapter and this quote, but also in my opinion, the whole chapter and the whole report fails to grapple with is what kinds of errors are not okay in science. When have we gone too far? When have things gotten too bad that we can say this community, this discipline is, doesn't have the safeguards in place, is not acting responsibly, needs to change. And that's what I felt like. I don't know the answer to that question. How do we know that? But that's the question we need to be grappling with. It's not the question of, do we have no errors or some errors okay? Of course, some errors are okay. Of course, sometimes things won't replicate. But if we're not asking ourselves the question of how do we know if things are worse than they should be, if we're making unforced errors, if we're allowing things to get through that really shouldn't, if we're making the same errors over and over again, for example, if we're making errors that are very preventable, or if we're punishing and stifling criticism that would lead to a more accurate scientific record. A more kind of explicit and more specific to my field reaction to this replication crisis was some authors, very, very prestigious authors. So I don't know if you have this in physics. We have an annual review of psychology where it's by invitation only, and you kind of write a summary of the state of the field. And so some of the most eminent psychologists were asked to write about the state of psychology in the kind of peak years of the replication crisis in psychology. And so they wrote, all of this replication crisis is normal science, not crisis. A replication failure is not a scientific problem. It is an opportunity to find limiting conditions and contextual effects. Of course, new studies don't always replicate. And again, I agree with that in many cases. I think that is absolutely true in a healthy scientific discipline, but there is no burden here on the discipline to question itself and ask, are we a healthy scientific discipline with a normal amount of error, normal amount of self-correction, or have things gotten too bad? And in this case, I think my big beef with statements like this is that these statements are made by the very same people who, when the applications were coming out, when the problems were coming out, were not cheering and saying, hooray, this is science self-correcting. We're actually trying to create obstacles to this kind of work getting out there, the criticism getting out there. So the same people who are saying all of this is normal science, of course science makes errors and it's good that we're fixing them, are also people who were using words and phrases like these. These are actual names that replicators and critics in psychology have been called during the replication crisis. There's only a very, very partial list. And my favorite is this one, accuracy fetishist. Sorry, the slides are advancing on their own. And I want to find, so one of the ones on this list is human scum. And that sounds, and I can laugh about it, but at the same time, I literally had a reporter call me and say, a famous social psychologist that you definitely know said about you, I think they're human scum. What do you have to say about that, right? So this has gotten very, very personal. And so it's a bit weird for these people to then turn around and say, let's pat ourselves on the back for being a self-correcting science, right? So one of the things that has come out for me is when I teach undergraduate research methods and I talk about scientific values and methods and so on, and science being self-correcting, I now feel a much harder burden of explaining, well, how do I know that our science is self-correcting? How do I know, what are we doing to make it self-correcting? And I'm not okay with just saying, this is normal science, any kind of error is okay. We often see the first few panels of this comic, but it doesn't go well if we stick with this line. So I've been, partly because I teach undergraduate research methods and wanted to have a better answer to this question of, I can't just stand up there and say, take my word for it, science is self-correcting. So how do we know? And I've been reading some philosophy of science and other work on this. And there's a historian of science, Naomi Oreskes, who I really enjoy a lot of her work. And she came out with a book in 2019 called Why Trust Science. And I was very excited to dig into this and see what she says about what makes science self-correcting. So she talks a lot about some of the values of science and how they're different than corporate values or other kinds of values. And so she gets to the point in the book where she's going to talk about, how do we know that science has these self-correcting mechanisms? And she says, well, we know the same way we know other empirical phenomena, we observe them. And she says, when we observe science, when we observe scientists, we find that they have developed a variety of practices for vetting knowledge, for identifying problems and attempting to correct them. And again, this sounds good, but it's very kind of generic and vague. And I was not very satisfied with this. I would like to find a more concrete answer of what are these mechanisms and how do we know they're there? And how would an outsider be able to tell if a field didn't have these safeguards and these mechanisms? We can't just take a field's word for it. We can't take, even as insiders of the field, we can't just rest on our laurels and be confident that we have these mechanisms if we can't point to them and say, here are the ways in which we encourage detecting errors and fixing them. And from someone in psychology and biophysiology, James Heathers, here's his take on the self-correcting mechanisms in science as someone who has identified many, 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 many errors in the published literature and tried to get them corrected. He says, in reality, mechanisms to correct bad science are slow, unreliably enforced, capricious, run with only the barest nod towards formal policy, confer almost no reward and sometimes punitive elements for a complainant who might use them. And this is my experience too. And I have to admit, as now having been editor of several journals, seeing things from the inside, I'm fully with the critics here who say that journals and editors often don't do their job, often don't take self-correction seriously. And not only do we not reward the people who point out errors and try to fix the record, but we often make life quite difficult for them. And so now when I teach research methods, I emphasize that this idea that science is self-correcting is a claim that needs to be tested in itself and something that needs to be supported with evidence. And science is self-correcting, sure, this is also James Heather's, when we correct it, not because of magical progress, right? So I've been working in recent years a lot on the kind of the practical side of philosophy of science, that if we want to make our field better, what should we do? How do we earn back our credibility? And so thinking about this question of why trust science, what makes science trustworthy? And here there's some useful information from social science surveys. So for example, Pew has done surveys of representative samples of adults in the US and also in other countries, but these data are from the US. And we know from the Pew data that trust in science is quite high and trust in scientists is quite high. So these are the green bars here over time. This doesn't go into the post-COVID era, but I think that the numbers may have dipped a bit, but still trust in scientists is quite high in the US and in many other countries around the world, and higher than or equal to basically any other institution, trust in any other institution. But interestingly, in those same surveys, they also ask respondents questions like, do you think that scientists are accurate and fair? Do you think that they admit their mistakes and take responsibility for them, and so on? And the public is not naive. So here's how they respond when asked if scientists admit and take responsibility for mistakes, for example. And so the green dot is the percent of respondents who agree that scientists admit and take responsibility for mistakes for different kinds of sciences. And you can see that it's fairly low. 10 to 20% of respondents agree that scientists admit and take responsibility for mistakes. In my opinion, that's completely accurate because scientists are human. And if we've learned one thing from behavioral and social sciences, it's that humans are not very good at admitting and taking responsibility for mistakes. So that's not why science is trustworthy. And the public trusts science, but at the same time is not naive about this. What makes science trustworthy is not that individual scientists are noble and superhuman and completely able to admit their mistakes. Instead, I think philosophers of science and sociologists of science are converging on the idea that what makes science trustworthy is something about how we check each other's work, about our social process. And this is something that actually a psychologist said a while ago. He said the dependability of scientific reports comes from a social process rather than from dependence upon the honesty and competence of any single experimenter. Organized distrust produces trustworthy reports. And organized distrust is an idea from the sociologist of science, Robert Merton. And so the idea here is that we don't count on each of us to be objective and accurate. We count on the social processes amongst each other to catch any problems. And so for that to work, we need two fundamental things, in my opinion. We need transparency. I'm not sure why this. Okay, we need transparency and we need this idea of organized distrust. And so to take a metaphor here, transparency would be like saying that you have to lift the hood on the car. You can't try to sell me a car without showing me what's inside. So if you want me to take your claim seriously, tell me all the details and show me the materials of what you needed to obtain those data, and then show me the data and the code that you used to analyze it, answer any questions that are reasonable questions that people might have about it, et cetera. So transparency is good. It means that you're not hiding anything, but it doesn't necessarily mean anyone's going in and checking it. What organized distrust means having a culture where you incentivize and reward people who actually go in and do the work of stress testing the important results and checking if they're robust and so on. And so what I would argue is that at least in the social sciences, where we've had this kind of replication crisis and this coming to terms with our problems, we've made quite a bit of progress on transparency. So in this pyramid of, the culture change that Brian Nosek made, where he talks about, the first steps are to make something possible, make it possible for people to share their data or to register their analysis plan ahead of time or other kinds of transparency. And then we move towards making it easy, making it normative, making it rewarding. In the social sciences, we're not yet at making it required, but we're working on it. And it won't always be required in every single case, but we're working towards making it the default, that we assume that someone should be transparent unless there's a good reason not to be. And this is important. It's been challenging even to get here. There's been a lot of resistance just to increasing transparency. A lot of like, why are you asking us this? Do you not trust us? We're creating a culture of distrust and things like that. And I think it's been really important here to go back to basic values and talk about, well, what do we tell the public and what do we tell our students? If we're not willing to be transparent, then what makes science different from any other kind of knowledge? So I think it's important here to really remember our roots, remember our commitments and our basic principles. And I think transparency is quite uncontroversial if you go back to those kind of basic values and foundations. So even though this was quite hard to get where we are in the social sciences on transparency, there was a lot of resistance, and we're still fighting a lot of these fights. We still have made quite a bit of progress, and that's good. But transparency is only the first step. And as Andrew Gelman has said, he has a great 2-page paper that I strongly encourage, especially for trainees. Honesty and transparency are not enough. Actually, not specifically for trainees. I think senior people need to hear this even more, but it's just a very easy paper to assign, very short. He says, consider the consequences for a researcher who eagerly accepts the message of ethical and practical values of sharing and openness, but does not learn about the importance of data quality. They could then just be driving very carefully into a brick wall, conducting transparent experiment after transparent experiment, and continuing to produce and publish noise. So just lifting the hood on the car doesn't mean that there's no problems. We need both transparency, but then we also need a culture of going in and checking those things and making sure that we care about quality, that we detect errors and fix them. And as hard as it was to get traction on transparency and make the progress we've made, I would argue that organized distrust is going to be even harder. And part of the problem here is just human character. As Kurt Vonnegut put it, another flaw in the human character is that everybody wants to build and nobody wants to do maintenance. Many people go into science because they want to make discoveries, not because they want to fix other people's false discoveries. But it's worse than that. It's not just that it's maybe work that isn't at the top of all of our lists. We actively deter people from doing this kind of work, and there are disincentives to do it. So while we may be nearing the top of the pyramid on transparency, I would say on organized distrust, it's often not easy and sometimes even not possible. People try to correct the record and nobody listens, or they're kicked. Basically, the punishment is that they no longer are able to function in the field because they've become so unpopular. So how can we encourage more organized distrust? So if we want to say that as a field, we're fine, we don't have a replication crisis, we don't have a credibility problem, then we need to make sure that we're encouraging organized distrust, that we have a culture of it and that we reward it. And so here there's kind of different ways to think about it. I'm going to take this car metaphor too far. So in psychology, we have a little bit of physics envy. And so we developed something called the psychological science accelerator, borrowing from the concept of accelerators in physics. Part of the concept here is just to do really big team science to accomplish things that we wouldn't be able to with individual labs and individual PIs. But I also kind of like the metaphor of accelerating science, that part of the purpose of these kinds of big team approaches is to push the boundaries of science, to go further and faster than we could otherwise. And I think that's a very noble goal. We absolutely need that. But as we know, when we accelerate things, there's also the chance that things will crash and burn. And so we shouldn't just be going full speed ahead and not caring about, error control and quality control. So my argument is that any field that has functions to accelerate science should also have repair shops for broken or potentially problematic findings and so on. We need to have a place where we can take a finding that, let's say the field is running away with it, building on it, but it hasn't been stress tested yet. Where are we going to take it to do the stress testing to find out, is it generalizable? Is it robust? Is it, and again, the specifics of what that looks like will be different in different fields. But we have to have the infrastructure, not only in advancing and pushing the boundaries, but also have infrastructure for slowing down, checking, correcting, and having people who are rewarded for doing that well. One question is, who should do this work? And there's some argument that it should be part of, for example, early career training, that before we go on to do novel experiments, maybe we learn to replicate other experiments, and maybe those findings should make it out there when there's been some quality check on them and so on. I think one thing to think about is that it's really important who is in this dialogue about criticism and organized distrust. And this has been pointed out by many of the same philosophers of science who talk about how objectivity in science is achieved through this organized distrust, the social process. They talk about the importance of diversity in these communities of organized distrust. And this is, again, Naomi Oreskes, the historian of science, but she's talking about ideas by Helen Longino, a philosopher of science, where she says, the greater the diversity of a community, the greater the degree of objectivity it may be able to achieve as individual biases and background assumptions are outed. And here the idea is that if the critics have the same biases and blind spots as the authors and as each other, you're not going to catch all of their errors. In order to have really effective organized distrust and a community of criticism, you need people from different backgrounds with different blind spots, different assumptions, different theoretical commitments, but also different other kinds of commitments and experiences, in order to have a better chance of detecting different problems and getting to a more accurate overall answer. So if we're going to make early career researchers do a lot of this work, and we're going to make people with different backgrounds and maybe from underrepresented groups do a lot of this work, then it's even more important that we protect and promote the people who do this work and not, impose a lot of penalties on people who detect errors and bring them to light. Felipe Romero is another philosopher of science who has a paper called Who Should Do Replication Labor, where he argues for a specialized career track. And I would say it applies not just to replication labor, but any kind of error detection and correction type of labor. And so he talks about what we would need to do in order to make this a viable career track. Right now, I think the incentives are such that it would be crazy for anyone to try to make a career, at least in psychology, and I suspect in many other fields, to make a career out of trying to make the published literature better, just identifying errors, identifying areas of improvement, and so on. But these are the people doing this are the people who allow us to sit in front of the public, in front of our students, and say science is self-correcting. We are committed to self-correction. So we need to be able to say that. I think that is a really fundamental value in science and a fundamental thing that makes science trustworthy and valuable. We should be able to pat ourselves on the back and say science is self-correcting. But if we're going to do that, we need to put our money where our mouth is and actually support and reward the people who allow us to be able to say that. And so I would say the takeaway from psychology's replication crisis, the main thing is that it's not that we had these problems, it's that we weren't looking for them, that we would have been defensive about the idea that we had these problems, and that we didn't react so well when they were first brought to light. And I think if physics wants to learn from our mistakes, I would say cheer on the people trying to identify problems and trying to assess the state of the field, because those are the people who make it possible for you to say as a field that we're committed to self-correction, we're credible science committed to accuracy. So I'll stop there. Thank you.
Okay, thank you, Simine. That was a wonderful talk. We have some questions from the audience, which I will list the ones that are there. If people have more questions, I think you can use the hand raise feature. I think you can't unmute yourself without me doing it. So just raise your hand and we'll get to you. Let me start with the first question from Lee Smith, which is there a historical record on this question? Can we tell that the replication problems suddenly got worse, or were they there all along?
Yeah, that's a great question. So on some dimensions I'll take replication broadly. On some dimensions, there is a historical record. So for example, transparency. So we know that, for example, in psychology, it was extremely rare for authors to share their data. Part of that was just the technology wasn't there. It wasn't clear what it would have meant to share our raw data in the 1980s, for example. So we can track that things have gotten better. And even just since 2012, let's call that the beginning of the replication crisis in psychology, we can track that things have gotten a lot better on transparency. They're still very far from the ceiling, but they have gotten better. Other dimensions like replicability itself, I don't think there's a lot of data. There weren't audits of the replicability of psychology, at least prior to the first one that I know of was published in 2015. So part of what we're doing now is trying to do a lot of meta-science to establish the baseline now, so that in the future we can repeat these same audits and see if things have improved. But looking backwards, I mean, psychology is a fairly young science, so it's a little bit harder to say, but there isn't a lot of meta-scientific work prior to the crisis to know what things were like back then. Some things we can go back and code, like what kinds of methods, what sample size people were using, for example, is a big deal in psychology. We can go back and code that, and things have improved over the last few decades in psychology. But most of that work is only being done now. There wasn't meta-scientific work on that before.
Okay, thank you. Another question comes from Michael Weissman. He says, of the 2/3 of registered replication attempts that didn't pass the p less than 0.05 criterion, how many had actually statistically significant data from the original? So how much of the problem was just having different data versus looking at or treating the data differently, or drawing different conclusions from similar looking data?
Yeah, so many of the replication projects were careful not just to use a p less than 0.05 criterion, partly because many of the replication projects actually were much, much more highly powered statistically than the originals. So that almost was a meaningless criterion, because you could get a p less than 0.05 result and it'd be extremely inconsistent with the original. So there have been different kind of criteria and different people developing new kind of thresholds for what do we call consistent with the original. So that literature, I would say, is much more nuanced than I gave it credit for here. I would say the bottom line conclusion doesn't change if you use a different definition of replication success than p less than 0.05. And actually, over time, from 2015 to more recent replication attempts, the authors of the replications have gotten better at not just using that p less than 0.05 cutoff. So the discussions have increased in their sophistication, I would say.
Okay, maybe I can use my co-organizer privilege to sneak a question in myself here.
Sure.
I wonder how much of the business of addressing a replication problem comes down to just training people in more advanced statistical knowledge. Like, I think those of us in condensed matter don't really appreciate how hard it is to infer causality in a statistical sense. So how much of it was just psychology people needing to learn more statistics?
Yeah, I would say if learn more statistics includes things like understanding reasoning about causality, then yeah, I would agree. I think it depends how narrowly you define learn more about statistics. I think some of the problems are much more about research methods more broadly defined, understanding the difficulties, like how rare it should be that we make a claim that something is generalizable or that an effect is causal, or, there's many of these kind of grand claims that we think we can make just based on statistical error control or something really a narrow definition of statistical validity, when in fact there are all these threats to validity that come not just from statistical errors, but other kinds of errors in reasoning, errors in theorizing, and so on. So, I mean, I guess in a way that absolutely it comes down to not good enough training on validity and inference, but that's just science, right? Just we're not doing science well enough, I guess, is another way of saying that. So it's hard to argue with that. But it's complicated to say it comes down to training, because honestly, like what I found as editor is that the worst offenders are often the most senior people who in theory should have the most training and so on. Of course, it would be great if we could make the next generation much better, but it's almost pointing the finger in the wrong place to say that the trainees need to do better, because really we also need to figure out how to fix the problem from the top.
Okay, thank you. Another question here from Anna Akrap, who asks, what, if anything, can be done about status bias?
That's tough. But I think one thing I've been talking a lot about, because it's one of my passions, is that we in psychology, we talk a lot about wanting transparency from individual researchers, that they post their data, their code, et cetera. But we should also expect more transparency from the gatekeepers and the decision makers. So in my field, journals are quite reluctant even to name the handling editor on a paper. That should be completely uncontroversial. You should not be editing if you're not willing to make it public that you were the handling editor on a paper. And that would already start to bring to light potential conflicts of interest, or other problems in who's handling whose papers and so on. I think we should make the content of peer reviews public. Reviewers shouldn't have to sign their name to it if they don't want to, but what was in the review should be public, so that when a paper is published, everyone can see how thoroughly it was vetted. Did it seem like it was vetted thoroughly? Did it seem like maybe the reviewers were in cahoots with the authors and so on? I mean, that won't catch everything, because sometimes reviews look fine, but actually there was a conflict of interest or something like that. But at least it holds journals and decision makers more accountable. I'm quite shocked at the extent to which we've pushed for transparency from researchers, but we allow really big, important decisions to be made completely in secret. Now, of course, some secrecy is warranted. As I mentioned, I'm not for forcing reviewers to identify themselves. I think that the fear of retribution and so on is real. So sometimes there are good arguments for not being 100% completely transparent, but journals, professional societies, funders, et cetera, there's a lot more room for them to be more accountable for what they're doing and whether they have safeguards in place for status bias, for example. So what are their policies around conflicts of interest? Can editors publish in their own journals? And what happens if they submit to their own journals? That's another big avenue for corruption. So all these potential areas of status bias and corruption, we should ask our societies, our journals, our decision makers, what are you doing about it? And what can you show us to help us have more confidence that you're, doing something about this problem?
Okay, I have one more question from Aaron Hui, and I'm worried that you only have 1 minute to answer, and it's going to be a hard one. So do your best in 1 minute. His question is, how does one build a proper incentive structure to fix replication problems? At the moment, it seems we have a method, but no real way to reward it or incentivize it.
Yeah, I mean, I would point you to Felipe Romero's paper at that table that I showed. I think he outlined some ways, but ultimately it's going to come down to money. We have to fund people. We have to build career tracks and make those career tracks, protect them to some extent from retribution from the people they're criticizing and so on. So funders can fund correction work, not just novel discovery work. Universities can hire those people. We can promote them and bring them to the top of our search committee lists and things like that. But also some of it is just the informal protection that we do by helping with networking at conferences and other ways that we help our trainees, making sure that we're doing that and looking out for the people that are doing this kind of work, who are probably going, there's a lot of whispers behind closed doors and stuff about people doing this kind of work. So the more we can do to protect them against that and give them the advantages that others are getting, I think that's part of it too, the informal stuff, as well as money and formal positions and so on.
Okay. Simine, thank you very much. A wonderful talk that I think in condensed matter were very needed to hear. So thank you again. So in the interest of trying to make sure everybody gets time to talk, let's move straight along for James Hamlin from the University of Florida. James, if you can share your screen. And meanwhile, I'll just, okay. Yeah, go ahead. James Hamlin from University of Florida. Why don't you just take it away?
Okay, can you hear me okay?
Yep, we hear you fine.
Okay, great. I'm recovering from cold, so if I stop to cough, please forgive me. So this title of the talk, Extracting Data from Scientific Publications, is kind of a story of a personal journey of dealing with some issues with publications and trying to figure out how to really get at the data that's inside them. So I'm going to review a few different topics here, kind of beginning with an old European paper that I was a part of, onto this carbonaceous sulfur hydride room temperature superconductor, some recent findings about manganese disulfide, and then just some sort of personal thoughts that have come to me after being involved with this for a couple of years now. So let's begin with europium and kind of going back in time. One of the last things I worked on during my PhD was this PRL paper. Debesai was the first author. And I had been involved in some early measurements that kind of weren't ready to publish. And after I went on to be a postdoc in San Diego, Matthew Debesai finished up the measurements and found this very nice susceptibility data plotted here on the right. So these are voltages from AC magnetic susceptibility coil, where when you cool below the superconducting transition, there's a sudden drop in the resistance as the flux is expelled from the sample. And so we found the paper reports both anomalies in the resistance, although not complete drops in the resistance, and then these nice susceptibility transitions. And so now I'm going to jump forward in time over a decade to another paper. So this was a very low temperature superconductor. In 2020, this paper, Room Temperature Superconductivity in a Carbonaceous Sulfur Hydride, came out. And this paper reported results using the same susceptibility technique. Again, these are nanovolt measurements. So you see a drop in the voltage as you cool below the superconducting transition temperature claimed. So here the temperatures are much higher. So these are up close to 200 Kelvin, very, very high temperature superconductivity. I was quite excited to see this. My former colleague, Matthew, was a co-author, and it was beautiful results. I looked at this data and it looked like just about the size I would expect the transition to be from the information given in the paper. The noise levels were sort of what I expected. Everything looked exactly as I thought it should, according to what I knew about this AC magnetic susceptibility technique. Okay, so why have I mentioned this 2009 paper and then this 2020 paper? Well, soon after this room temperature superconductivity paper came out, Jorge Hirsch began asking questions about it, and he spoke to me about the magnetic susceptibility because he knew I had done these kind of measurements. And in those conversations, he eventually began to question the superconductivity in europium. And he published this archive article that pointed out what he called remarkably similar curves in europium and in the europium and CSH papers. I've taken the two curves that are under question here and tried to make them look as similar as possible by scaling the X and Y axes. And I did not find this very convincing that this was the same data. Of course, there was some question about the upturn here. In europium, you might expect that from polyparamagnetism or from paramagnetic susceptibility tail at the low temperatures, but in CSH at much higher temperatures, you wouldn't expect that. But I didn't find this particularly compelling, but nonetheless, in this article, he pointed out a possible reason for this similarity being a common author. And I thought this was premature to highlight that, but nonetheless, it turned out that he was right. And so I'm going to explain the issues that were found in both of these papers. So after we were pressed for the raw data, eventually that data was discovered on an old computer, and I obtained that data. There were 65 raw data files, an origin lab file that was used to produce the plots in the PRL paper, and I also got scans of a laboratory notebook. And when I began looking at this, problems became apparent very quickly. If I looked just at the origin lab file, there was really nothing there that pointed to problems. But when I began looking at the, beginning from the raw data files, things became clear. So this plot here shows the coil voltage versus temperature, and it basically shows the series of steps that's necessary to transform sort of what was measured into what was published. So here, the blue data is what was published in the PRL article, and the orange data is what should have been there, or what was actually there in the data. So the first step is you scale the transition to 49% of its initial amplitude. You then subtract a line from that data. Now we can see that this portion of the data, so I'm sort of modifying the orange data step by step to get to the blue data. So we line up down here, but there's still this area of disagreement. So next you have to delete that data, that little blip there. And then you have to take this portion of the data, just this higher temperature portion of the data, shift it down by 60 millikelvin, and then you have to subtract a constant from that to get to this data. Now you get perfect agreement. And because I had all of the data files in question, I was really able to, through performing this series of steps, get perfect agreement between the data published and the data that I was able to obtain through this series of steps. So that was one example for the 111 GPa data. Here's another example for the 142 GPa data. So blue is what was published in the PRL, and orange is what was actually in the data files. So here you can see essentially what's been done is this whole thing at low temperature has been sort of gotten rid of here. So the first thing is it's scaled to 52% of its original amplitude. Then we add a line. So now you can see this high temperature portion of the data lines up. And then some of this low temperature portion of the data was shifted up. So now we get agreement here. But there was still this puzzling region in the middle here where I couldn't figure out where that data had come from. So right here, I had no explanation for this. What I did was I took all 65 of those raw data files, and I took a set of data points, and I compared some segment of data points against every other segment of data points in every other one of the 65 data files. So this script took about 15 minutes to run. I then took the difference between the shifted data and the original data, calculated the residual, and then sorted kind of the files and the line number offsets by residual. And very quickly it popped up a certain portion of data where this data clearly came from. And so it came from a different data file and a different temperature range. So data from down around 2 Kelvin, irrelevant to this data up around 2.5, was simply copied and pasted up into this region. And you can see that very clearly by comparing the data up here with the data down here from this other file. Okay, so what was the reason for these anomalies? So there's clearly something happening in the data. Where was it coming from? Well, it just so happened that a postdoc working in my group had spotted some similar anomalies just a few months earlier and figured out what they were. So at the time, we were using a gas-loaded diamond anvil cell. So essentially, there's a helium-filled membrane. And by applying a small amount of gas pressure to this membrane here, you can push the diamonds together and obtain a much higher pressure inside the diamond anvil cell. Well, at high enough pressure of the gas, the helium in here at low enough temperatures can freeze. And what my postdoc Isaiah Lim recognized was that some anomalies he saw in beryllium gold matched very well the melting curve of helium. So when the helium solidifies, there's a small change in the force, creates a small change in the pressure in the cell, and that can then create an anomaly in whatever you're measuring. And so if you plot the anomalies in europium, both the susceptibility and resistivity anomalies agree quite well with the melting curve of helium. Okay. So there were two things going on in this problem with this paper. There was an artifact due to this feature, which the interpretation was then obscured by altering the data to make it appear to be very consistent with superconductivity. So the outcome here was that the paper was retracted. So not only did we find that the data had been altered, but one of our co-authors also repeated the measurements using a cell without a membrane and didn't find that the superconductivity was there, confirming that these features were likely due to superconductivity, were likely due to this artifact from the pressure in the membrane. And you'll notice this sentence that the data presented in figure 2 were not accurately reported. So this is a statement that we could get everyone to agree on. And when trying to get a retraction published as quickly as possible, getting everyone to agree on it is a necessary step. So this experience was obviously very stressful. Retractions, it's hard to not feel anxiety that the retraction is going to affect your reputation. But I think being open and honest about what actually happened in this case is the best that I can do. So let me now move on to carbonaceous sulfur hydride. So with this europium paper now retracted, there was additional pressure to obtain the susceptibility raw data for this room temperature superconductivity paper. And that data was eventually published in the form of over 100 pages of sort of low resolution images of tables. So this was not a particularly easy way to get at the data, although initially thinking it might be a lot of work, I found that in about a half a day, I was able to get the data out. You know, you have a one-liner on the Unix command, you know, on the Linux command line will dump all of the images out of a PDF paper. And then another one-liner will do OCR on all those pages and dump it into a series of files. And then you can simply plot the data. And occasionally there'll be errors in the optical character recognition, but they immediately become very clear when you plot the data, and then you can go back and look and correct the data. So, okay, so even if it's not the most convenient form of presenting the data or making the data available, really any way of making the data available is helpful for assessing the reliability of it. So I'm not going to go into a huge amount of detail about the problems with the susceptibility data because Dirk van der Marel has another talk associated with this workshop that goes into greater detail about what was found. But on the left here, we have the susceptibility data. And this 160 GPA data, when you look in the paper, you don't really notice any particular issues here. However, with access to the data files and the numbers, these sort of strange artifacts became clear. So if you look at this plot here, panel C, that comes from this region sort of down here somewhere. And then this plot up here comes from a region up here, right? And so you see what looks like kind of a smooth curve connected by these jumps. These jumps turn out to be all the same size. And you can then think of just lining these all up. It's rather straightforward to write an algorithm that does that automatically. And what you find then is that there is a smooth curve here. And so when I saw this, I was able to reproduce this quite quickly, and I found that this smooth curve was a cubic spline. Van der Marel and Hirsch also independently came to the same conclusion that this was a cubic spline. Now, initially, people who saw this had a sort of a charitable explanation of it, which was a reasonable one, that perhaps what had happened was that the authors, when they did a background subtraction, so let me explain the background subtraction briefly. At high pressure, this is a very, very tiny sample. And so this transition, particularly in low temperature measurements, could be riding on a large background. And so typically what you do is you measure at a nearby pressure where the TC is at a different temperature, and then you subtract the two measurements from each other, and you get rid of most of the background. I think what some people interpreted this as is perhaps the authors had used a cubic spline or some kind of smooth curve as the background. Perhaps they fit their data with the spline and then simply subtracted that spline from the data being digitized as any data from a digital instrument is, would then take on this kind of shape. And that's a fairly reasonable thing to think. So I don't think this by itself is really a clear indication of a definite problem. But the problem comes when you look more closely at the data published in that archive article I showed you, where optical character recognition was used to extract the data. So in that paper, they published both the published data and the raw data. And so if you have the published data and the raw data, it's quite easy to obtain the background that must have been used, because the published data should be the raw data minus the background. Okay, and then this is where things become hard to understand as just a simple background subtraction of a spline. And again, Dirk van der Marel has given a very nice presentation on all the reasons why that explanation doesn't make sense. I will give you my kind of short version of that. So the authors state that the published data is the raw data minus the background. So what we see here in this plot is temperature. And now instead of just the voltage, we have the difference in voltages. So this is the difference between the voltage of two adjacent data points. And the published data here is in blue. And what you see is that it sort of goes up here. So this is plotted in the vicinity of the superconducting transition. So this peak here is where the susceptibility is rapidly increasing. Okay. And then the raw data is also what was put in that archive article. The background is what you find by using this equation. Okay. So now what you find is that the published data has these very discrete increments indicated by the gray lines here. So it changes by mostly these increments of, I think, around 0.16, 0.17 nanovolts, all right? Now, to suppose that the published data is the raw data minus the background, we have to somehow assume that you take this sort of random raw data and you subtract this random background data, and somehow you now get this perfectly digitized data. And I simply can't understand how that could happen. And the authors have offered no explanation of how that could happen, although they've repeatedly said that they have offered an explanation. It's not there in anything that's been published in an understandable way. So the straightforward explanation here is that instead the raw data is actually the published data plus some kind of background measurement, which is some kind of noisy measurement. So obviously, if the raw data cannot be raw data, it sort of calls into question this whole result. Okay, so these kinds of concerns and others, I think, eventually led to the retraction. So the paper was retracted. They say here that the details of the background subtraction were not specified in the paper. The authors maintain the raw data provide strong support of the main claims of the original paper. So sometime later, or during this whole process, in February of 2022, I had raised concerns also about the electrical resistance data. And I requested the raw resistance data via the Nature editor and didn't receive it. So having gone through that process in February, I was somewhat surprised to see in September the following quote in this article that appeared in Science. Another senior member of the collaboration points out the retraction does not question the drop in electrical resistance, the most important part of any superconductivity claim. Well, at that point, I had questioned the electrical resistance data in the paper. Here is the electrical resistance data in the paper. And so the question is, how could I get at this data if the authors did not share it? Well, it turns out that both of these plots are plotted in a vector graphics format in the paper. So what that means is that if you zoom way in on the plot, it sort of remains sharp. So here you can see a contrast between a raster or bitmap plot and a vector graphics plot. They've both been zoomed way in. And so here, as you zoom way in on the raster plot, it gets kind of blurry, right? And this plot is just using kind of a grid of pixels to define the data. So there's no information about this blue curve that goes underneath this black data. There's no way that you can get at that blue data underneath this black curve. As I was sort of looking at these plots and zooming in to very high magnification to try to see what was going on, I noticed that my PDF program sort of rendered the data very slowly. And you could actually see these data points kind of gradually appearing, particularly at high zoom. And so that gave me the idea that, really all the data, even the data, say, behind these yellow points, is somewhere in the file. It should be accessible, right? So somehow this type of plot is generated by a set of instructions that tell the computer where to draw the lines on the page. And so somehow you ought to be able to get at those instructions. Okay, so can we extract the data using vector graphics instructions? So the answer is yes. You can read about that in this archive post, which also has a link to a GitHub repository that contains all the methods used to do this, all the methods used to generate the plots in this paper. There's also a Zenodo repository that has all the data that I extracted using this method. So what are the steps? Sort of briefly, you can take the entire page of a PDF and you can convert it into what's called the SVG format using a utility called PDF to SVG. So this stands for Scalable Vector Graphics. It's basically a XML file. Then you can look at the plot, and you can use a color picker, or another program that's quite useful is Inkscape. You can figure out what the color is of the particular kind of data point that you're interested in. And then there's a Python library called SVG Path Tools, which has some useful features that allows you to pull out various paths from the SVG, and you can then filter them by color, or if you could, for example, filter them by the number of edges. So if you wanted to distinguish rectangles from hexagons, that would be fairly straightforward. So you then compute the centroid of all those vertices of the path to find, where the data point actually is. Or in some plots, you've simply got line segments, which are sort of rendered as a single path with many different sets of coordinates in it. So here's an example of a red data point. Once you've got the file in SVG format, you can simply open it with a text editor, and you can look at all the instructions. You can search for values with particular colors, and it becomes a puzzle. It's not straightforward, but you can do this. I'm working with a student now to try to make this into a more sort of general use tool, like the old data thief, where you could open a plot and then there'd be a set of options to allow you to extract different types of data. So at the moment, it's fairly labor intensive to pull this out, but you can even do things like find the coordinates of the tick marks and use that to get a very accurate calibration of the data points, of the plots, of the scale. So I wanted to confirm that this method works. And so the way that I did that was using some data where I had access to the raw data. So I picked something recent, a 2021 PRB article by Lim et al., where we measured pressure-dependent superconductivity in beryllium-22 rhenium. And if you look at this 15 GPa data curve, that's the one I elected to extract. And the reason for that is that a lot of the data is hidden by other data, both in the high and low temperature regime. So using something like Data Thief or this web plot digitizer, which is a common tool people use, you'd never be able to get at those data points. However, using these methods that I just discussed, you can in fact get at these data points. So here you can see some data points here that are obscured in this region that are extracted with very, very high fidelity. And then again, down here at low temperature, that 15 GPa curve is completely obscured, but you can still extract the data quite accurately. So here the blue are the raw data points, the ones that I had access to because this data was collected in my group. And then the orange is the data that was extracted. And you can see that it's not perfect, right? So here the raw data shows a bit of a difference, but the extracted data does not. That's because even in the SVG file, the coordinates are not stored with infinite precision. In order to keep the file size small enough, there's some truncation of the digits. Okay, so here again are the data from the CSH paper. It just so happens that both plots show the same data set from 267 GPa. So here we can extract from both plots and see how they compare to see, to assess the fidelity of the extraction. So here's the original plot from the paper. Here's one generated after I extracted all the data, and you can see that you can zoom in on this region here, and you get all the data out, even though the points are overlapping in that region. So here's a small, a zoom in of a small segment where both data sets are, both the data from two different figures are both available, and you can see it agrees very well. And we see this very unusual digitization artifacts, very similar to those in the susceptibility data. There's sort of smooth data, and then these discrete jumps that all happen to be the same size. So you can disentangle these jumps from this smooth part, just like was done for the susceptibility data. So here's the susceptibility version. So the green is the published data. You can disentangle it into these discrete jumps and this smooth cubic spline. And something similar can be done here for the resistivity data. So again, it looks like essentially there has been some background subtraction. So Diaz and Salamat explain these susceptibility artifacts in this archive article as being due to, they say this effect is a consequence of the user-defined background. Of course, in resistivity data, there should be no background, and certainly none is stated in the paper. Okay, so I'm going to jump very briefly to something more recent. I will say that after I expressed these concerns, future resistivity plots from this group in later papers were all in raster format so that I could not use this method. So I started looking at some older data, and I found this manganese sulfur 2 paper, and I was comparing it to the dissertation of one of the co-authors, and I found what looked like very similar data sets. So we have here 13.5, 16, and 24 GPA data on germanium, selenium 4. And here we have 13, 16, and 26 GPA data on manganese sulfur 2. And these look really remarkably similar, considering these are completely different compounds. So I extracted the data here. I'll say that if you cite along the curve of this green curve in the paper, you can see this little blip here, even without digitizing it. But I used my digitization methods. And so what you see here on the left is sort of the full temperature range of data, where manganese sulfur 2 and germanium selenium 4 have been plotted on left and right y-axes with different extents, right? And so I think immediately it's pretty clear that they're very similar in a number of ways, although there's more curvature at high temperature for germanium selenium 4. However, if you zoom in just below 120 Kelvin, you find that the data agree almost perfectly. And so we can look at that in a little more detail here for one of the low pressure measurements. So again, even these little kind of double wiggles here are present in both data sets. The blip, which when you look just at low temperature, very clearly resembles this. So I should be clear that in this paper, the only issue I found was with the resistance data. So let me make some concluding remarks here, which are sort of thoughts after having gone through this experience of dealing with all these issues for some time. So concerning the CSH data, in the absence of better explanations, the most straightforward conclusions are that the raw data is derived from the published data for the susceptibility, that the electrical resistance data has been subject to some kind of unstated background subtraction, and that the electrical resistance data for manganese sulfur 2 is derived from data on germanium selenium 4 earlier published in the PhD dissertation of Diaz. So, okay, so the CSH paper has been retracted. So why is this relevant? Well, there are a number of very remarkable claims coming from this group about near ambient conditions superconductivity. And so these authors should address these 3 items above and approach their future claims with full openness about their methods and what's been done with the data. So some last kind of conclusions about reproducibility. So I think we certainly need a culture change about publishing raw data. I'm not sure how to bring that about. The steps to produce the plots should be fully documented, ideally in some kind of script, Python or MATLAB script that takes you exactly from the raw data to whatever published data or graphs you have. And then, one idea, excuse me, would be to have a reviewer whose sole charge is just to confirm that the data and analysis are properly archived and documented without really assessing their validity. So those items are rather difficult to implement. One that's very easy to implement is that journals should require graphics to be submitted in vector format whenever possible. This is a very simple step that requires little additional effort. Most journals have a statement that this is true, but if you actually look through those journals, you find that relatively few plots are actually presented in vector format. And then finally, maybe perhaps a silly idea, we need a journal of negative, incomplete, and boring results, which would help reduce pressure to alter or over-interpret data. So I think in economics, there's a journal called a series of uninteresting results in unsurprising results in economics. And so we need to find a way of rewarding people for getting their data out there, even if they haven't come up with a brilliant and exciting interpretation of it. That will also prevent wasted and replicated effort. So, okay, I will stop there. Thanks, everyone.
Okay, James, thank you for this pretty heroic story. I think we all appreciated it. Okay, we have a couple questions. We have about 4 minutes before we have to move on. One came early from Babak Saraja is, how did the preprints repository like archive, what's the role that it played here? And for example, a lot of us remember that Jorge Hirsch was banned from the archive for engaging in this business. Any comments you want to make about how the role the archive played in all of this?
I mean, that's a fairly broad question. I think the archive is obviously very, very useful. I think there's a problem where the discussion becomes contentious. I think there needs to be some kind of method to comment on papers in a more, perhaps if papers had a commenting feature on there. I mean, there is PubPeer, but I think PubPeer has a stigma. It would be nice if there were a way of discussing and commenting on papers that didn't have quite the same stigma.
Okay, here's a question from Peter Armitage. He says, James, I was unclear on the timeline. He may have missed it. The comment from Salamat was after you brought your analysis to the attention of the Nature editors or before?
The comment where they published the raw data was before I was in contact with Nature editors.
Okay, I have a sort of personal question for you. Like this stuff that you're doing took a lot of time and effort. Was it like stressful to feel, or did you feel like you had to put your other research on hold to do this, or were you staying up late at night doing this? Like, what was the cost of doing all this stuff?
Yeah, I mean, it was extremely stressful, of course, at the point that it was tied up with, the retraction of a paper on which I was co-author. It was extremely stressful, and that was a driving force behind, trying to figure things out. I think I can take away from it that I learned a lot about data analysis. So I learned Python while coming to all these conclusions. So I can take that away from the process.
Okay, sorry, one more question, Peter Armitage. Can you give any thoughts on how the europium data was falsified, or how has your co-author explained himself?
I think there's a combination here of, an artifact that caused misleading data. And then there was, in my opinion, an effort to make that data look 100% convincing. I think that, I guess the thought that keeps coming to mind is you can't outsmart nature. And it's okay to be wrong as long as you present the data accurately. But as soon as you stop presenting the data accurately, you're asking to be fooled. I can't speculate on the psychology behind what happened.
Okay, Peter points out that you can, in fact, outsmart nature if by nature you mean the journal. Okay. Okay, I think that's pretty much all we have time for. James, thank you very much for this wonderful talk.
Thank you.
Okay, Vincent is next. Vincent, are you ready?
Yeah, just a sec. Can you hear me?
Yes, we hear you just fine.
Just a second. Having too many screens here, losing my mouse.
Yeah. Okay, this is, while he's setting up, this is Vincent Mourik, who's from Forschungszentrum Jülich. He runs a lab focused on developing quantum devices for quantum information applications. And he's going to talk to us about what's going on in the field of Majoranas.
Can you see the presentation fine?
Yes, please go ahead.
Okay. Thank you for the invitation. Thank you for the opportunity to present what I consider research. It's carried out together with Sergei Pollock, one of the organizers today. And I have a fairly lengthy talk, so I will try to go through it all. I first want to set the stage tonight. Sorry, it's night here. So a bit of history and why this is such a complex research topic. Then I want to go, that's the bulk of the talk, into actual what I consider case studies. And then some concluding remarks that will be brief, hopefully, at the end about some more generic remarks. So this is about Majorana fermions. It's actually a beautiful story, a story that captured me when I started the research back in 2010, and I still find it a fascinating story. So the Majorana fermion is a highly mysterious particle, and the man himself is also very mysterious. You can read all about it. He disappeared. The particle is mysterious because, as a fundamental particle, it has never been found in nature. Part of that is perhaps because it's a particle that has very little measurable properties. It's equal to its own antiparticle. And we love to use this analogy, the painting by René Magritte, where it's also very mysterious how the mirror image of the person can be equal to itself. Now, how did this enter solid state physics, condensed matter physics? That is a decades-long development that started in the 70s and then sort of accelerated from the late 90s, early 2000. And this has a really solid theoretical foundation. These are well-known, well-understood models, toy models, I should say. And what they predict is that the same field equations in particle physics can be applied to condensed matter systems, and one can get the same quantized solutions from it, quasi-particles now. No longer fundamental particles, so they're electronic state, collective behavior of the condensed matter system. So this evolved in the years 2000s and actually became increasingly more realistic. And by the time of the start of my PhD, there was a proposal out there. It is 13 years ago now, I think, roughly, that this appeared at the March meeting, more or less. And that it looked like we could implement it. Now, another really exciting aspect of this research, genuinely exciting, is that these are different from, fundamentally very different, richer almost, I would say, from the fundamental particle physics, from the elementary particle physics version. These Majoranas, particles, quasi-particles in solid state systems, they have a very peculiar property. If you have an ensemble of them in a system, they form a quantum ground state. And by moving the particles around each other in the terms of moving their world lines around each other, you're actually changing between different ground states of these particles. And from an informational perspective, from a quantum computing perspective, this means you can encode information in the quantum ground state. And by moving the particles, the world lines of the particles around each other, you are actually performing a quantum computation. This process is called braiding because of the intricate pattern that the world lines form. And it's supposed to be resilient to noise because the pattern itself can be deformed and shaken, but to break the pattern, you need to cut strands, basically. So there's this combination of beautiful fundamental physics and potentially technologically attractive applications. And this was all known in 2010 already. I learned about this at the start of my PhD. So we set out to implement this research. It was a very exciting time with the team, real team effort, hard work, but we got early results after 1.5 to 2 years in, got published, deserved a lot of exposure. So all looked fine. Then, as it turned out, and it's the next topic I want to put emphasis on, is that the research turned out to be very complex. And how can we understand this? So typically, that's very typical in condensed matter, of course, is that toy model serves as the inspiration. So we have a simple formula with a bunch of terms. And then as an experimentalist, you look at that, how can we implement that? So what do? You look at all the various systems these terms represent. So what do we need to add? Superconductivity, complex semiconductors. These need to be made, these complex semiconductors. So material synthesis is what you need. And you need electronic nano device fabrication to shape it into the right geometry. And then you need to do cryogenic measurements. So this is actually very hard to make. And it's a real challenge as a team to get this done. And I can really confirm this. I've done this. It's hard work. But it is possible. And you can make them. But it comes with the typical troubles, I think, that are well known in this type of research in condensed matter physics. Individual devices cannot be exactly reproduced. If you make your device so complex, it means you have many experimental parameters, typically about 5 or 10 knobs that you can turn. Makes the experiments complex. It's fairly costly to make this. The combination of fabricating the devices, assuming you have the facilities in place already, and having the setup, I think it's easily order 1 million for one of these experiments. And the measurement itself is highly complex, takes months. So what this amounts to is that it's hard to do statistics. It's hard to gather many data sets from many nominally identical devices. The other thing is that everybody is fully aware of this, I think, experimentalists and theorists. You never implement the toy model. You do something inspired on the toy model, but it's not the same. It's something different, something way more complex, something real life, honestly. It's like a cartoon versus the real thing. So that also means that theory has to and can develop itself by making the theory models more complex. So typically in our community, this means that you go to lattice models where you do complex numerical modulations, where you simulations, where you model your device as realistic as you can. You introduce more and more variables to try and map your model to the experimental reality. And of course, this is finite what you can achieve. It's infinitely extendable in principle, but it's, you know, beforehand, it's impossible to fully simulate a device. It's just not possible. It comes with programming complexity and computational time. So the same deal there also theoretically. Resources limit you in the end what you can do. And this begs, of course, the question, and how do we connect the two? How do we bridge this gap? And this is very challenging, actually. There are no established protocols for that, as far as I know, in our research in condensed matter physics. At least not in those subfields that I'm aware of. And this, I think, immediately lead to the major pitfall, and regardless of this is theory or experiment, is that there is a tendency for extreme fine-tuning and biased data selection. And why is this such a big issue? Because potentially viable alternative explanations actually do exist, and we are aware of them. So this leads sort of towards the end of my PhD, and I want to use this particular, which is sort of a counter example to the physics sphere after this experiment, to introduce you to some of the typical data. So what you can see here in all these color plots is electrical conductance, so the differential differentiated current. Oops. That's a color scale, so red is high conductance, blue low conductance. Horizontally, there is typically a parameter varied, so it can be a gate voltage, can be a magnetic field. Vertical axis, we have bias voltage, which translates typically to energy, more or less, one-on-one. And the point is that for Majorana fermions, we look for something that sits in the middle here at 0. So the conductance is low here because this is a superconducting system, so the spectrum is gapped. And we want to sit here in the middle and find a high conductance there because we have this special Majorana state sitting there. That's not enough. We want it to be robust. We want it to be insensitive to minor variations or even major variations of this horizontal axis. Now, why is this such an important experiment? I think to our community, the authors implemented a very similar device, almost identical to the devices I made in my PhD as a student. And what they found was that also these states, which are clearly discrete states that move slowly, gradually together, that they can also linger for a little while at zero energy, at zero bias voltage, and mimic the behavior of Majorana bound states, Majorana fermions. Now, this was I think the whole community had digested this a little bit and accept this. That took a couple of years. It took me towards the end of my PhD, 2015 or so, to I think, start embracing this idea. I moved out of the actual research topic. For my postdoc, I did something else, also in CondMed, but not the same topic. But then, of course, you keep watching your old field. I kept talking with Sergey, etc. And what we noticed that more and more claims are being published, follow-up research on our own research, but in some, looking at the papers as published, listening to the talks, not everything added up. And that brings me to my first case study, so to say. That's actually from my own PhD research group. This is about a paper which has been redacted in 2021, I think. And it was an important paper in the field. The claim was that a special type of zero bias conductance, namely the conductance, was quantized now. You can read it here. The height of our zero bias peaks remains constant despite changing parameters. That indicates that it is quantized, and that was a hard prediction from basic theories that this should happen when you have a Majorana fermion. And this is how that looks in the paper as published. You can see that upon applying a magnetic field, one of the necessary things to do to make Majoranas in these nanowire devices, you can see that there is the conductance is here going up. There's these states coming down that form a zero bias peak, and it plateaus for a little while here before dipping down again. So that's as a function of magnetic field. And you take a crosscut, and you see a plateau also as a function of gate voltage. So it looks good in the relevant parameter space as something stable, something robust. So we asked for additional data because we had questions, got some in the form of a PDF file with color plots in it. Later down the track, also numeric data was shared, but initially when we performed our analysis, it was based on color plots of the data. And basically then we spent a couple of weeks stretching and matching graphs between the paper and between those between the additional data files shared with us, the PDF file with the color plots. And really, I think the main find and the most striking find is that for relatively small variations of parameters, some are a bit larger than others, but nominally this is all in a similar regime. You can see all these panels. This is always magnetic field on the vertical axis and bias voltage on the horizontal axis. Now I flipped the plot here. And you can see that you have these states coming together, forming the zero bias peak. What you can see that sometimes it appears as a crossing, sometimes it lingers a little bit, but you have this, this somewhat consistent behavior across all of them. And the point is that actually only 2 of the plots that are present show a conductance of order 1 times the conductance quantum, the value you need. Most of them show a higher or a lower value. A factor 1.5 different, more or less. So this is a case of critical data omission. I think if the community would have seen all these plots, we would not have believed that the peak was quantized. Now, if you look at the gate dependence, the other parameter that was varied, you can see it took a bit of detective work, but you can match up all the pixelations in this data set up here and down here. You can see that matches with the pixelation in the published figure, but there's also differences. So there's been cropped, so the data set is cropped, and there's also this section in the middle that's been cut out, and this was non-disclosed. Now, why is that important? Because if you, these discrete jumps here, they're very common in these type of devices, and we understand them as random charges jumping around a little bit in the devices. It's sometimes a statistical process, just happens. Sometimes it's because you change a gate and then a charge trap empties or fills. And what they do, they reset somewhat the axis. They change the local potential landscape a little bit, so they affect your physical phenomena that you're trying to observe. Now, if we would have seen that right upon basically peaking, it immediately dips down again when a charge jumps, this would have been significant because it means that, what stops it from jumping all the way across here? Maybe there is no plateau at all. In fact, you can see here on the right side that it looks like the peak is splitting again. So perhaps all there is in this data is that you just have these two states, crossing a little bit, touching each other.
Sorry, Vincent, I think we're unable to see your pointer. If you have a pointer, we're not seeing it.
Oops, one moment. Thanks for pointing that out. Yep, can you see it now? Yeah.
Yes, now it's good. Thank you.
Yeah. So I was indicating these pixels here, and these are the discrete charge jumps that I mean. So you can see that cutting this bit here and cutting this bit here actually has an impact on the visual appearance of the phenomenon. Now it looks like a much more extended feature. Whereas in reality, if you look this as an experimentalist, if you have some experience dealing with this, you start to have questions. Is this actually anything robust in the gate axis? This is another very peculiar panel, is this small panel in figure 2E. What is done here, that you take horizontal line cuts in the plot, one at zero bias, where the peak sits, one above the superconducting gap, so at finite bias. You take the conductance values and you plot them against each other. So these values here correspond to this curve, and the vertical values here correspond to the curve in the center. And what you can see, that is the point of this figure, is that this is really flat. While the conductance here is rising, the conductance outside the gap, the conductance in the center of the gap where the Majorana peaks is supposed to be, stays flat. And the first striking thing is that if you compare another panel in the paper, you just compare them, you can see that about 70% of the data were excluded in the making of this panel. So when we got the numerical data, we could replot this. And what you can see, so this is basically replotting all these data points and keeping the same scaling of the axis. Okay, so that's another feature here, is that this is very different scaling compared to that one. What you see now is that this is basically a scatter plot without much flatness in it, if you accept that all points are data, but the yellow ones are the ones that constitute this curve. Okay, then you can even try to not take this curve, but the opposite one at the opposite bias, and you get yet another different shape. And you can see that there's actually more spread now in the superconducting conductance compared to the normal conductance. So in other words, there is no plateau here. And this was basically a combination of omission of unfavorable data points and a misleading scaling. And the last example I want to use from this work is figure 3, where they show the conductance in the center again of the peak. And this is a very strong statement written about this particular curve, namely that the zero bias peak comes back up to the quantized value, which is 1 in this curve, and does not cross through it. So something could affect it to bring it down, but it does not cross through it. And right at the point where the curve in the paper ends, the full data set continues, and you see that it crosses by a factor 1.5 through the actual value. So you can find there's some more details. I've shown you some striking examples, but you can find that in our independent analysis, and there's also an independent expert panel which confirms our findings, I must say. And this is a second paper, and this is mostly a material growth paper with actually interesting growth in there and interesting advances. But to make it really the breakthrough, I think, that made it into Nature, they needed also confirmation from electrical measurements, electrical transport measurements. And of course, they find in the paper that the device, that the material is great and that it is suitable for, observing Majorana fermions, establishing them, and then subsequently braiding them. That is the storyline of the paper. However, the paper figure 4 and some of the supplementary data that reports the electronic transport measurements, again, it is suffering from significant data omission. So cropping, but also lines have been deleted, to the effect that these bright vertical stripes that you see here are not being shown. And these are widely known in our community, and they are typically associated with uncontrolled, random, unwanted quantum dot features. It is localization. So it is the opposite of having a very clean device through which electrons can move unhindered. Instead, electrons are obstructed by potential barriers and they localize. And this basically means that, well, the growth is, of course, what it is, that is true. the electronic characterization measurements are not reliable. And this was the cause for the paper to be retracted. Now, the third example I want to show is, because it's slightly different in flavor, I think, it is selection of what devices to show in the paper to make a claim. So this is a chip, a fabrication run of 20 devices, where 4 were selected for inclusion in the paper. And what is significant here is that the ones selected don't show clear vertical stripes, but the ones non-selected, many of them do show these stripes. And again, this is because of generally understood due to unwanted quantum dot formation, and the claim of the paper is that this is not happening at all. Now, when you see this happening, when this occurs, then you need to ask yourself the question, why do I then select these devices into the paper? And this question has not been answered well in the paper. Yeah, I can't go into all the details of that. You can find that in this Zenodo analysis. Yeah, so this paper is under investigation. We have recommended it to be retracted. I'm a co-author actually on it. I wasn't aware of these issues at the time of publication. And yeah, whatever happened to it, I want to retract my name from this paper. So what is the status here is that there has been no evidence. We did not find anything of data fabrication or data falsification at the basic level, but there were a number of undisclosed data manipulation steps that had significant impact. The most impactful aspect, in our opinion, is crucial data omission, so selective bias representation, and this has caused unsupported claims. So the current status is that the 2 papers retracted. We have recommended 2 additional ones for retraction. There's a number of additional papers, about order 10, I think, that we think should be investigated. Some do raise serious questions. And thankfully, Delft is releasing more and more raw data, although it is going very slow. But yeah, it is happening slowly. So I hope that in the near future, this can be closed, this topic. The second case I want to show is from a different institute, but very similar type of device. So now we again have a one-dimensional nanowire, but it is covered conformally with a superconducting shell. Actually very interesting, nice devices. Cool to study, I think. If you penetrate the cylindrical shell with flux and you put a flux quantum in it, the theoretical prediction is that you get Majorana fermions in these wires for odd flux quanta in there. So we had some questions about this paper as well, and we requested additional data from the journal, which we eventually then got some additional data, and we looked into it. So the main claim of this science paper is actually has nothing to do with Majoranas. It's purely phenomenological. The claim is that this is again a map of conductance. So dark is low conductance, bright is high conductance. Here now we have flux on the axis, and here we have bias voltage, so energy if you wish. Here, for zero flux and low flux, when we don't have a flux quantum yet, we have a superconducting gap that slowly closes, and then as you put an integer number of flux in there, it reopens again. It's a beautiful effect. It's known for quite a while now, but it's really nice to see it in these mesoscopic devices, in these nanowires. But the statement is that every time you have 1 or 3 of these flux quanta in them, so the odd lobes of this pattern, there is a robust zero bias peak. So robust against magnetic field variations and gate variations. So the upshot is that this is not generally correlated with these oscillations. So we find in the same device, we find also examples of split peaks. In another device, which is nominally identical to the same device, we find a fork. So first it forks and then it becomes a zero bias peak. In yet another device, which is considered a negative device in the paper, there is also no zero bias peak here. So these 2 plots are from additional data that were not present in the original paper. So if I zoom in a little bit more on this feature, there is a strong statement about the behavior in this first lobe at finite magnetic field, namely that this zero bias peak, this is from the paper, this zero energy state it represents, is present throughout the tunneling regime. Okay. Now, if we look at the more extensive data shared with us, we find actually that the gate voltage range is not significant. We find instead that the blue line here represents the gate range. The two measurements are not exactly identical because of a charge switch in between. What we find in this particular scan is that the yellow boxes contain a zero bias peak and the green boxes don't contain a zero bias peak. And okay, this is the high conductance side, so who knows what happens really. But here in the tunneling regime about which the claim is being made, actually for most of the tunneling regime, there is a split peak. There is no zero bias peak. And this is in plain contradiction to what is written and shown in the paper. Another questionable aspect is what is a bad device in this research? So device 5 is being considered bad. There's some reasoning behind it. One aspect is that it doesn't show the desired feature, the zero bias peak in the first lobe. The other one is that it shows these discrete states in the superconducting gap at zero magnetic field. And then there is a reasoning behind that. However, device 3 is considered a good device in the paper, but this large data set was not shown in the paper. And what you can see is as a function of gate voltage, it's arguably messier in terms of states that are crossing through the superconducting gap compared to the other device. So what does a positive reproduction device mean versus a negative one that contradicts or that is a negative result in your study? What is really important in this case is that there have been independent reproduction studies. So this group from IST Austria, the authors here, they have actually obtained the identical nanowires from the same, nominally identical, it's not the same wire, of course, you cannot reuse them, from the same grower, but it was the same growth batch, I believe. So they made nominally identical devices. This is the closest you can come to reproduction in our community, and they performed the same experiment. And that it is a reproduction study is basically clear by looking at the data itself. Because if you look at this typical pattern, gate voltage versus bias voltage, and you look at all these winding states inside the gap, that's essentially the same as what you see in most of these devices when you look at the extended data from the work from the other team. Now, what they find is that it's, in our opinion, a more extensive study. More data is shared, at least with us. What they find, they put the spotlight on these winding states, and they show that indeed for very small, very small but somewhat extensive parameter ranges, it's still of the order of hundreds of millivolts, you can find lingering zero bias peaks. But it's completely interpreted in this paper in the framework of these trivial Andreev bound states, which cross as a function of parameter changes in the experiment, and then sometimes linger a little bit at zero bias, mimicking the behavior you expect for Andreev bound states. And I want to actually, I saw comments in the chat that reproduction studies are never being published in the same high-profile journals. Well, in this case, it's actually different. The original paper was in Science, and this reproduction study, negative reproduction study, one may say, got published in Science as well. So here we have a positive case. And actually that continues because there is a second reproduction study of the same type of experiment, and that got published into Nature from the same team. Now, what is different here? This is a different type of measurement. Now, the device is the same. It's still this nanowire with the shell around it. But now we look at the length dependence of the devices. So you need to make many devices and shrink and shrink their size. And what you look for is the energy splitting between zero bias states. So you have states that are at very low energy or at zero bias, and as you make the device shorter, they start to split. And the physical mechanism behind this is that they start interacting with each other, and Majorana fermions, when they start overlapping, they start, splitting away from zero energy. There is when you do that length dependence, there's a very specific prediction from a simple theory, namely that it should be an exponential decay. Whereas if it's non-Majorana, it should be a power law decay. This is already a methodological issue, I think, in itself, because you have very few data points. You can question what to do with these very small splittings. You can question what to do with very short length, because the theory is perhaps not applicable when you make devices as short as the wire diameter. So in the end, you are left with a bunch of data points in the center, 2, 3, 4, and you try to distinguish these two different dependencies. It's already not easy. But in the reproduction study, what is, I think, really a crucial find is that they found that in these vertical columns, they kept the length fixed. It is the same device, but they found a huge spread in the energy splitting between the states they were probing. Okay, and this is basically, it can go all over the place. And what is differing here? It is caused by gate tuning. So not the length. The length should be the one that affects the energy splitting, but no, it's changing the gate voltages here that actually hugely affect this energy splitting. So this measurement is prone to fine-tuning. The other thing they find in this reproduction experiment is that it does not need to correlate with a localized state here. And that is the simple picture with Majoranas, that you have them sitting at the end, and as you make the device shorter, they have to overlap and start to split. That picture is not applicable because they see these splittings in their measurements. They can measure that while not having to see local states at either end. So apparently this is a property of, somewhere in the middle, or the bulk of the system, rather than the localized end states. So these are all questions that I think apply to this, the second half of this paper, but also to two earlier papers. Okay, so what is the status here? I think the problems here are very similar to the Delft case, but we did not find the type of data manipulations in the Copenhagen work. Instead, we found cropping and we found crucial data omission. But the effect, this is why we think that this is perhaps the most crucial one. The effect is the same. The claims are unsupported. Now, I want to point at one of the satellite talks. There's a reproduction study being discussed there of another work from this team, similar in spirit, also nanowires, with a slightly different implementation. So the status is that the science paper, we think it should be retracted because it's not valid. We have concerns about multiple additional papers, but data requests are being consistently refused. So we basically cannot do anything, despite, I think, valid concerns that we have. Now, the last case I want to discuss is somewhat different in the sense that we have not done a deep investigation. It's a very complex experiment. It's been fairly recent, but I think it's important to discuss it here as well. So again, the device is very similar. It is a nanowire type experiment, very similar in implementation. And the idea now is to measure locally on this end, and look at the bulk of the system. So you want to see a zero bias state here, you want to see one here, and you want the bulk of the system to undergo a superconducting gap closing and reopening. And only when you see those three things together, you will conclude that you have found a topologically non-trivial phase with corresponding Majorana fermions. And this is formalized in a rather elaborate, complicated theory, also a fine-tuned theory. That produces a protocol how to implement this. Fine-tuned, it has 25 or 30 parameters, so it's really one of these complex theoretical models. Now, two basic observations and things I want to point out. First is that the local measurements here are rather what we consider messy. You can see many of these bright vertical stripes again, which we tend to associate with localized Andreev bound state due to charge confinement, and then you get local Andreev bound states in these devices. Now, supposedly, their protocol is robust against that, but I want to point out that this is all present here. So you can expect the trivial physics to play an important role here. The next thing I want to point out is that when they perform the protocol and when they find regions where all these three things happen, so where all the where the zero bias peaks and the gap closing and reopening coincide, this actually is extremely fine-tuned. The relevant range here really is the gate axis. This is about sub 1 millivolt in width. And this is the largest one I could find from the paper. Now, if you then have a conversion factor from gate voltage to actual energy in the devices, that's typically a factor 10, maybe 100 even. That depends how strongly it's coupled. So we're looking here at a feature that is tens, maybe 100, few hundred microvolt in width, which is really small in terms of localization physics. quantum dots live on the scale of millivolts, typically in these devices, in energy scales. So it's completely reasonable to me, at least, that as a consequence of this elaborate fine-tuning, you found the features you want, you're after, but that it could still be caused by disordered physics. And as a matter of fact, independent theory groups have been fine-tuning their non-topological models, and they can produce similar predictions. So this is not, we have not done a full analysis of all the materials available. Recently, they did share those. We did not get to that yet. There's a live journal club we did on this paper that you can find on YouTube. Those were the 3 case studies that I wanted to mention. Now I want to close basically with a few general remarks. So are the problems more widespread? This was really focused on nanowires, but there is a lot of research going on topological superconductivity and Majorana fermions. So there is another satellite talk, and I recommend you to watch it. It's also a notorious case, I would say. There the data was actually fabricated. This is about topological insulators, quantum anomalous Hall. So this was a very serious problem in another system, but more generically speaking, and I want to point at this disclaimer, this is not about particular papers at this stage. It's about generic philosophy of the research. I think many of these systems and many of the measurements we perform in them are prone to fine-tuning and biased data selections. For example, vortex cores are supposed to host Majorana fermions under the right conditions. How do you select which vortex to represent? How do you rule out trivial Andreev bound states? Interferometry with non-abelian statistics. It's a 2 decades known problem by now that it's extremely difficult to rule out Coulomb physics, electrical confinement related effects. Re-entrant supercurrent in certain Josephson junctions, sometimes associated with topological phases. But how do you rule out trivial effects? Shapiro steps to prove the 4-pi Josephson effect, another prediction of Majorana physics. Why is this also happening in trivial samples? What are the conditions under which this can happen? Can we establish actually, is it a valid method to claim Majoranas? So I think the situation is challenging and somewhat sad and worrisome. At the same time, I'm doing this because I care about research, although I'm not currently doing active research in my own team on the very topic. I still think it's beautiful physics that's worth investigating, and we should continue pursuing it. And in that sense, I'm an optimist. I think we can do better. So, and this is generic, I think, not only to this research field, but to all research fields. And many of the things have been said in the 2 previous talks already. So I think we should foster an open science culture, standardize sharing of full data, research protocols where relevant, analysis protocols, open publishing. So make the peer review publicly visible, at least the arguments, not necessarily the names, but at least the discussion. We should really normalize critical discussion, prior to publication, when something is shown at conferences, when the paper is in peer review on archive, also post-publication. Why are we not accepting a critical dissemination of work? Be critical of overly complex experiments. We have sometimes just too many control knobs, and it can lead to fine-tuning or overfitting. Verification and reproduction research. It's currently not funded, not really rewarded. Like you get some kudos for it, but it doesn't show on your CV really. But it takes a lot of time and effort. When you think there are problems, focus on the science primarily. Like that's the main thing we are after: establishing what science, what results we can trust, and how to move on. But ultimately, I think this requests a broader cultural change, some maybe even throughout society, not just in science. Less hype and breakthrough orientated, less single person, single team. It should be more collaborative. And I really hope we can, as a community, improve our work style and efforts there. That's at least what I will strive for. Thank you for your attention.
Okay, thank you, Vincent. Unfortunately, we've used up pretty much the whole time before the panel discussion. Let me just ask you one very short question, I think, if you don't mind. One, I think I understand from you, and correct me if I'm wrong, that to your mind, there has been no convincing demonstration of Majorana physics in any situation. Is that correct?
The honest answer is simple yes.
Okay. Is there anywhere where you think that what is seen could be Majorana's that just hasn't been proved? Or do you think that everything that has been demonstrated is ruled out by a skeptical eye?
Well, this is Occam's razor. I think it's a very healthy, normal principle. Why use the complex hypothesis if you have a simpler, more mundane one that we know for many decades that is around that can explain everything? Mm-hmm. But in principle, that is the problematic reason for it. That's why why we bias ourselves, why I got excited in the beginning of the PhD when was much less awareness for all these problems. Yeah, of course, when we see the zero bias peaks, it could always be Majorana's, potentially. And that's why you start performing all the cross-checks. So you need to do in-depth, thorough experiments, look at the data as a whole, look at the full evidence, and then try and draw your conclusions based on that and share the full data. And accept it when later on it turns out that the alternative does also explain your data. Then go back in your feedback loop, basically. That is my attitude towards it.
Okay, any last burning questions before we get to the panel? Okay, if not, Vincent, thank you very much for a very, very nice overview. It's funny, I've heard many people claim that we have definitely observed Majorana's because there have been 12 papers saying that we do. And people don't realize how much work goes into vetting these things. Okay, sorry, one quick question. Gil Kalai asked, are there some attempts to study the Majorana? Sorry, there's some attempts. Okay, sorry, Gil, I guess I didn't understand your question. Is there some attempts to study Majorana phenomena that cannot be achieved? Okay.
Oh, if it cannot be achieved in principle, I think is what is meant here. I think it's basically impossible to answer that question in the sense that the toy models work. They are valid. We know that. And it's beautiful, rich physics in there. And under the right circumstances, it should be possible.
Let me jump in as a... Oh, go ahead, Gil.
No, I just... it might be possible that there are some physical reasons that you cannot achieve them. I should say that I tried to understand them and to model them using quantum computing, and I didn't find any such reason. But I do have some suggestion for reason in principle why topological qubit based on Majorana mode cannot be achieved. But maybe there are some other ideas why this particular state cannot be achieved in realistic physics situations.
Yeah, so since it's my field and I'm also a co-organizer, let me jump in one time during this workshop. So I think just the existence of Majorana is based on a very simple theory that must be true. However, it is a mean field theory that makes some approximations.
No, I don't ask if the theory is true. I just ask maybe there are some additional constraints on what you can achieve.
Yeah, so let me comment on that. So I'm aware of at least one work that I find interesting is by Tony Leggett from Urbana, where they look into this sort of non-abelian property, and as far as I understand, question that. So maybe just the basic topological thing can be realized, but who knows? Once we get to the non-abelian, and I think you also say the qubit might never be achieved. Who knows? Maybe we'll find that the actual non-abelian experiment is impossible.
Okay, so let me just point out that Tony Leggett is in the audience, and if you would like to comment, let me know. I will allow you to unmute. You don't have to if you don't want to.
Very. Can you hear me? Try to.
Yes, we hear you.
Okay. We in a recent paper we did in fact give some reasons why we believe that much of the analysis of Majorana's in two-dimensional P plus IP Fermi superfluids, much of that analysis is based on mean field ideas, and we gave some arguments as to why the conclusions may not necessarily be valid if you try to go beyond mean field. If anyone's interested, it's in a new journal called Quantum Frontiers in the first issue of that.
Okay, thank you very much. Okay, I'm afraid I need to move us now to the panel discussion, but Vincent, thank you again one more time. So the way this is going to work is we have 5 panelists. I'll introduce them in a second. We're going to record the panel discussion up until the close of the hour, so in 50 minutes from now. And then we're going to stop the recording and continue for anyone else who wants to continue the discussion. The panelists are not required to stay past the hour. I only made them promise to stay until 3. So that's the way it's going to work. Let me just briefly introduce our 5 panelists. There's Igor Mazin, who's a theorist from from George Mason University. He wrote a very nice recent commentary on the inverse Occam's razor effect, which is how in our field we have a tendency to promote and publish fantastical explanations rather than simple ones. There's Lorenz Molenkamp from the University of Würzburg. He runs a lab that's broadly interested in electron transport. He was the editor at Physical Review B for about a decade, and I'm sure he's seen many retracted results over the course of his tenure. He was also recently involved in presenting evidence against that chiral Majorana paper that we just heard about that was retracted. David Muller is another person on our panel. He's at Cornell. He's an experimentalist whose group is broadly interested in materials physics. He was involved in pointing out misrepresentations in data from at least one Nature paper that I know of. And he also contributed to the investigation of Jan Hendrik Schoen and that Faribault Labs. We have Eugenie Reich in the audience. She's attorney at the law firm of Pollock Cohen, where she represents whistleblowers in cases of scientific and pharmaceutical fraud. She's probably best known to many people in the audience as the author of the book Plastic Fantastic, which is the definitive account of the Jan Hendrik Schoen scandal. And we have Jessica Thomas, who's the executive editor at Physical Review. She's been an editor at Physical Review since 2008, has been the executive editor since 2020. So my idea was to kick off the panel by making sure all the panelists get a chance to speak by just directing questions to them one at a time, and then we'll open up to questions from the audience and panelists can argue with each other. But I want to at least make sure that to start, everyone gets a chance to talk, introduce themselves to the audience. So Igor, we're going in alphabetical order. That means we start with you. Condensed matter physics is different than psychology and a lot of the science fields in that we have a prominent population of theorists, and a lot of our work is theoretical. And I kind of want to talk about to what degree theorists are involved or are culpable when we have replication issues. So to what degree do you see theorists as being culpable in driving sort of trendy narratives? And do you view it as an ethical problem when theorists are sort of promoting an unreliable experiment as a confirmation of some theory that they like? Okay, start with that. Take it for a few minutes as long as you want.
Okay. All right. So first of all, I think, as actually our first speaker alluded to, a large part of our problem is a human psychology, which is the same no matter whatever you are doing. I don't know, digging holes or doing physics. You always strive for success and sometimes try to cut corners. Like taking a metro at marathon run. You know that story. All right. So now, this I don't know about other fields, but I don't see why physics should be less or more prone, except that there might be fields like maybe pharmaceutical science, where just monetary rewards are much bigger and consequently temptations are bigger. So this said, the theory and experiment are not that much different. Particularly, if I posted something in the chat on that. I think it's in many cases that I'm personally familiar with, what we called fraud or manipulations doesn't really start as a fraudulent activity. Let me try to fraud my colleagues out of spite or something, or greed. It starts with somebody honestly believing that that's what they should see, or that what they should calculate, or that's what they see or should be. It could be experiment that really wants to reproduce a very fancy theory. It could be a theory which wants to explain an enigmatic experiment. And at some point, many of us are familiar with this feeling. You feel like, well, sure, I know that it should be this or that. And if I'm not getting that answer right, I might have a sign error somewhere. So why don't I just correct the science? Correct the sign error. That actually happened to me once, and the paper was accepted and was nearly published. And fortunately, before it was actually published, the columnist said, I was trying to reproduce your result, but I don't think the science is right here. I said, well, but then if you all understand intuitively what the answer should be, it would be not, well, maybe we don't understand it properly. And then we went through that once again, and I took this paper out, circulation, and then we rewrote it together. And I know other examples, again, a colleague of mine, he was presenting a talk at the APS March meeting. At the talk, another colleague stood up and basically pointed out a very distinct and obvious error in what he was doing. There's no question this is an error. And after that, I came up to him and said, what are you going to do about that? That nothing. The paper has been accepted PRL. I'm not going to throw out a PRL because somebody found a mistake. So now, again, so this is something which is common and we are trying to fight it. Now, there is a very few subset, a few people, and mostly they are known in the physics society who are actually actively pushing things. Again, another person I know, experimentalist at a very, very high rank institution, very famous, a young theorist, he was experimentalist, working with him, said he never ever I'm going to work with this person because he basically comes to me and says, your calculations have to give me this and that. And just no way how you how that can be wrong. And that person actually eventually published a paper where they wanted to support the interpretation experiment with some band structure calculations, which did not support the theory. So what they did, they just shifted by hand the Fermi energy in their bands by half a volt without ever mentioning or explaining that. So I don't know what you would call it, a theory or experiment. I know that they both were experimentalists. I know that the person who did calculations was a postdoc, fully dependent on the boss. And the boss said, I know that it should be this way. So if you're not giving me that, your calculations are wrong. So eventually he just manipulated his calculation, but he was forced into that. So what else can be added? Well, one thing, and then after that, several people did correct calculations. None of them was able to publish their result in a journal like Nature. And in some cases, the answer was just as explicit. Well, yes, we agree that this is that you found an error, but that doesn't make your paper strong enough for Nature or Nature Communications or even PRX or PRL. It's not that interesting. So I think that the last part is the biggest problem, whether it's theory or experiment.
Okay, thank you, thank you. Let's move on to our next panelist, if you don't mind. This is a question for Professor Molenkamp. I think a lot of us are worried about the question of whether things are getting worse. Maybe things are bad, but are they worse than they used to? So I wonder if you can give us any perspective about whether you feel like over the last 20 years, anything has changed about the way non-reproducible results are spread, or they're publicized, or are they falsified more quickly or slowly, or do you see a trend in time?
I think I do see a trend, but of course I cannot be totally sure because I only started out in condensed matter physics like 30 years ago. And I don't know whether I really had an accurate view of what condensed matter physics was then, but at least it was a smaller crowd. And you only published in VSF B or VSF letter. And only VSF letter if you had something really, really big. And for the rest, you knew each other and you trusted each other. That was the community I knew. I don't know whether that was correct, but that's how I looked at it at the time, coming in from chemistry. So that was a bit different. Yeah, so at that time, I really was impressed by the very concise way that I got told how to write my papers. Don't quote too many other stuff, just the relevant papers, not too much. Not just all your friends, not just all your own papers. And when publishing data, this was transport physics, they told me, only publish your raw data, nothing else. And that's something that kept with me forever, because that was a very worthwhile advice. And what you've seen today in a couple of illustrations already is that nobody publishes raw data anymore. And we spend our time trying to figure out how people manipulated it. And that's not a good thing. So when did it change? Well, I think it started changing late 90s. neoliberalism government, bureaucracy changing, wanting to have numbers in making their decisions. So before that, in judging quality of science, they actually relied on scientists they trusted, but that wasn't good enough. They wanted numbers, real numbers. And one number was given to Jorge, is also here at the use index. Well, that was a reasonable number. People could more or less live with it, but how to compare it between fields already became very difficult. It was clear very soon. And then the other thing that happened is that the government institutions that give you your funding started looking at where you published. And the impact index of the journals all of a sudden became really important. And at the same time, Nature had a clever editor who actually thought that one could build a good business on the impact index of a journal like Nature, because in Nature, it's not just physicists who publish and don't quote each other at all. No, there's also biologists and there's medicine people, and they always have tons of reference lists. So that's why the impact of Nature is enormous compared to the VSF letters where physicists publish their big stuff. And yeah, you start trying that, and lo and behold, you get in. And yes, the money comes. I mean, I've been there myself. I'm still going there because this is nice. Yeah, you get publicity, you get journalists phoning in, and of course your next funding comes in way easier. And that's what got it moving. And what I saw is also that, well, our field is getting more and more sexy for these docu journals. Other parts in physics are not as sexy. And that's why condensed matter physics is really in this whole business of mass publication and having fanciful papers way more than other parts of physics. And it's a bit, well, I see my old APS colleagues there. It's a bit of a shame that APS didn't recognize that condensed matter physics needs a different treatment than other parts of physics, simply because we are so exposed to this lofty paper issue thing. Now, so this is how this got started. And I think it's been on a gliding scale. And part is that if you want to publish in these glossies, it's all fine, but the glossies only want very short papers. So what you do is you publish 2 or 3 figures, select it carefully from your data, and the rest of the interesting stuff you dump in a supplementary material where nobody ever looks at. I mean, this is also something that's been very, very bad for the quality of reporting experimental research. Yes, we all want all the data, but dumping them somewhere where it's not really being properly reviewed and where people hardly can look is a very bad idea. And what we've seen now is that experiments, when they got more and more complicated, there's more and more data coming on, and people simply don't allow access anymore to a lot of the data that have been taken. So yes, this is a consequence of the fact that we really want to write very short papers and produce more and more data, actually. And it's very hard to keep track of all the data that you produce, to be honest. And even if you don't mind other people looking at it, you really need a system to store these data systematically so that they can be looked at. So yes, things haven't gotten worse, and I haven't seen any initiative from these glossies. I mean, they are trying to be, but I'm not impressed by the kind of things that have been going on with refereeing issues, making referee names notable. I also think we really need to make sure that we keep our own journals going, where we have referees that we can trust. And that's something that is not really going in the right direction for condensed matter physics, in my opinion. Something else that actually is also not going the way it should be going, as Brian indicated, I recently was involved in one of these Majorana issues, a paper in Science that was completely fake. I was very, very unimpressed with the way that the institutions reacted. Not Science. Science reacted actually quite well. Well, they couldn't do a recall because I was after 3 months, but in the end, they allowed us to publish a paper saying that we couldn't reproduce these results. And even later on, they were indeed willing to retract that paper based on the information I gave them. But what I really was shocked about was the reaction of the universities where these applications really went on. I went to them, gave them all the information I had, the information that was enough for Science to withdraw the paper eventually, and they just told me to go home. Be a good boy. They didn't think this was interesting. So it's not just the journals, it's also very much institutions that don't want to see that their prime researchers are people that are actually defrauding. Defrauding the taxpayer that gives them the funding for these nice institutes that these universities want to have. Yeah, so things have gone massively wrong, in my opinion. On the other hand, of course, we can still continue doing things. But for now, if I look at the fields where I'm active in spintronics and in topological materials, there is tons of incorrect papers in the literature, and nobody really cares. Well, what would you care? People make claims, whatever. You just do the things you want to do yourself. And every now and then, if things get really bad, you get into it. And that's what I've done now recently. But I know a lot more papers that are simply incorrect and are out there. And that's not a good situation to have.
Okay, thank you. I appreciate your perspective. David, I have a question for you next. Actually, I had some other question I was going to ask you, but there's one that came to mind as more interesting. For those of us who study like properties of materials, there's always this issue where someone who's growing a material will grow many samples, and then they'll pick their best sample and present that one, because there are many things that can go wrong when you're growing a material. To what degree do you feel like there's something dangerous or dishonest that can be done here? Like sort of like what Vincent was alluding to, that you make many nanowires and you pick the one that shows that you want. Do you feel like there's an ethical issue there or something that could be a best practice?
Yeah, I should say hi to Don Monroe, who was on the Schoen panel at Bell, and I see several Bell Labs colleagues here. We had a lot of lunch discussions with Schoen. And in fact, when I think of some of my interactions with Hendrik Schoen and some of his collaborators, there was an issue of, he had a collaborator who had made, 100 devices and was looking to reproduce Schoen's effect internally. And they made 100 of these things, and in 1 or 2 of them, there was something that maybe looked like something had happened. And in the other 99, nothing had happened. And this person was like, latched on to just the 1 or 2 that worked, neglected to mention the other 99 that had failed. And then, when we actually asked to look at one of these things, I just brought it into the lab, I looked at it on an optical microscope, and I watched the device actually peel off the substrate as we looked at it. So it was pretty clear it couldn't possibly have happened. And we're like, what the hell are you thinking? This is clearly pathological nuts. But, this was someone who was trying to reproduce desperately internally something that, Schoen had allegedly done, although, as Don will tell you, we had a lot of concerns about that. But, again, trying to get a result to work and cherry picking, by the time it comes to someone with an electron microscope, there's certainly a responsibility of your characterization people to make sure that you don't cherry pick your data. And I do have colleagues in the field who will show you an image, that's about 3 atoms across and claim to have a perfect interface. And there's a colleague, who produced some weird stuff a couple of years ago. And my students started talking to their student at the research conference. And their student sort of, said to mine, it took me a week to find a typical particle. And that was basically the, bad training from the professor that almost when I look at a lot of the misconduct cases that we've seen, in many cases, the person who did the bad stuff was a postdoc. But when you kind of look at their advisors, in many cases, that advisors had more than one person who's done bad things. And part of the problem, there was a microscopy case at a national lab where the advisor, I can point out several of his postdocs who did really bad things. And the blame I lay on the advisor is his view of the science at the most general level was, would order the postdoc to get the result he knew that he thought should be the right result. So in many cases, these were people who set out to prove something rather than setting out to disprove something. And that's a hell of a difference in how you behave and what you get pressured into after that. To even the point at one of their papers, when I asked the person who'd been caught faking data with beautiful duplicate curves that were mirrored and dodgy stuff like that, and what they said was, oh, my boss told me to produce a figure to convince the reviewer of what our data would have looked like if we had measured it. And we just forgot to mention that in the figure caption. The particular curve in question had error bars on it.
So sorry, if you'll allow me to return to my original question just for a second. Do you feel like there should be some principled standard that we should adopt of how you report and select your samples? And can you imagine what that standard would be? Like if you're going to make 10 samples, you have to report everything, all of them. Can you imagine some standard like that, or what would?
I mean, I would kind of hope that if you said, I grew something and it superconducted, you would at least want to mention just, how many samples it took to get this thing to work. Sometimes experiments fail for much more mundane reasons, but you'd kind of want to, certainly I make my students not give us, a zoomed in view of an interface. They have to show, in the supplementary, at least a 10 micron field of view. But, you would hope that with growers, you would have some obligation as to, how many, data points of what worked, what didn't work, because half of that's trying to get your phase space figured out. One thing that's been very helpful has been when people put their raw data plus the code that produces the raw data up as the data for the paper. I feel like something like that ought to be required if you want to publish, right? That it's sure your figure looks great, but show me the raw data that came off the instrument, hopefully in the raw data file that can't be manipulated, and show me the code that got you the figure. And at least if I've got those two things, you can go back and you can check for, is the result that they produced just Fourier filtered noise because they were too stupid to understand how to control the bandwidth on a Fourier filter. And I can point to a paper up on arXiv right now that's going to become some excited, twisted bilayer ferroelectric, and it's just Fourier filtered junk. But, I feel like our field was much worse off 20 years ago when no one had a capability of posting data. Now, at least the reputable groups will post data and codes. And the groups that refuse to do so, you can at least get a sense maybe something sketchy is going on with them.
Okay, thank you. Okay, I want to go next to Eugenie Reich, because you get a very different perspective, I think, sometimes from the consequences of, or who pays for when there's unreliable or even fraudulent results. So I wonder, who do you see being most negative? Like, we're sort of taking the scientist perspective, but who do you see being most negatively impacted when there's unreliable or fraudulent results that proliferate in the literature? And what do you see as the most effective system for guarding against those consequences?
Okay. Yeah, so as you said, I'm best known in this community for writing a 2009 book about Hendrik Schran's case of fraud. And of relevance to this workshop, there's a chapter in my book talking about the experiences of, I guess, about a dozen labs or so that tried to replicate the work. Mostly that wasn't their ultimate objective, just to vindicate Schran, but rather they wanted to get a working setup so they could do their own experiments, but they already could not get his setup working. And so I was speaking to graduate students, assistant professors, untenured, mostly untenured assistant professors, some more experienced professors and postdocs who were spending significant chunks of time. I say significant, but Schoen's case of fraud was reasonably constrained compared to some of what's been talked about or that exists, in that it took 2 years to publish 15 papers in Nature and Science and then bust. So that's about 2 years that people are trying to build on work that is completely made up. You know, a lot of people I see even in the chat are saying, well, this is egregious, this is a one-off. So let me just talk about what I think is maybe relevant to other scenarios out of the experiences of the people trying to replicate the work. And I think when Simine spoke at the beginning, she was right that a lot of it is not just the bad paper, the unreproducible paper in Nature or Science, but the informal, I guess she called it social process or something, but the informal interactions around the paper. So in Schoen's case, a lot of one-to-one interactions between Schoen and people at his career level or a little below or a little above trying to build on the work. A lot of misleading personal conversations, emails in which he first says one thing, go look at this parameter space, and then a few months later when they've tried that, go look somewhere else. This is actively misleading people and confusing and obfuscating in real time. A lot of, and the same at sort of talks by his collaborator Backlog, a lot of sort of misleading, whether on information from Schoen, largely about how the experiments were done. So it's not just the publication, it's what goes around it. And so, you know, a lot of people here spoke about negative behaviors like not sharing data, not letting samples be characterized other ways or cherry picking. But on the, so I wanted to talk a bit about why people believe any claim where that's happening to begin with. And so what happened with Schoen is a certain myth grew up very quickly that he has magical hands, that he's got supremely produced crystals grown at Bell Labs, an elite institution, and no wonder my lab can't compete, or no wonder I can't compete. And you know, this is a top institution. Backlog is a very famous guy who almost got the Nobel Prize before, and it's quite plausible might get it, might be part of something that would get it now. It's a sudden amount of myth making around that. So this is what's going on one side when the lack of transparency and data sharing and data access is going on the other side. And it's the combination of both together, which proved very problematic. And then, you know, in those days, I don't remember people talking about phrases like that Simine used, like status bias, or putting it in that framing. But that is an element where, you know, if you were at some significantly less famous institution than Bell Labs, and you started saying this kind of thing, you probably wouldn't get nearly as far before people stopped working on it and trying to build on it. So I think that's where those things intersect. So the experience, then you were asking who the victims are, people suffering from gaps on their resume, waste of their lab resources, funding agencies wasting money funding the labs to do that work based on false information. That's the kind of trail of victim, you know, that's where people are suffering, I think. And competitors who, as some people here have been saying, can't publish a less groundbreaking result because they're taking the time to do the work properly. And that's a type of victim too. And then I think you had a second part to your question, which is, something like who's responsible or how to prevent this.
What strategies do you see for mitigating against people being actively misleading? Like, it's a difficult question. I'm sorry. And you probably can come at it from a different perspective than some of us who are entrenched inside this business.
Yeah. So after I published my book on I'll answer that by what I did. After I published my book on the Shan case, I spent a few years publishing different reports and sometimes investigations, scientific breakthroughs or problems with scientific claims. And I eventually started finding, and this was when, social media was rising, that I think it was getting, so some of these situations were always covered up, right? But at least when they did come out in the public, there would be some satisfaction immediately. In the Shan case, within 2 years, the whistle was blown. The duplicate curves were in the New York Times. From then until the committee that Don Monroe was on publishing its report, thanks to what Bell Labs did, just a few months to reach an incredibly impressive public report by the institution. I can't think of, in 20 years, I can't think of anything comparable to that, which has to be somewhat shameful, particularly when you consider that was private money. And you guys are sitting at institutions taking a lot of public money and taxpayers' money and not getting satisfaction in terms of public reports coming out on what's really going on. So in terms of, I did end up going to law school, getting my law license. I've been involved in a couple of scientific fraud investigations, one in particular inside the government, where we were investigating a scientific fraud case in stem cell research. And some of the same factors existed. I can talk about it because it's closed case and because some facts were even in the New York Times, but this was a lab where they were putting up the virtuoso defense, as it's called. Somebody asked at a conference, why can't I replicate this research? And the answer came back, because you are not a virtuoso, meaning you're not an operatic star, right? You're not a talent. You're not a magical hands person or a superb crystals or an elite institution. This was Brigham and Women's Hospital, which is a Harvard teaching hospital. No wonder you can't do it. And that turned out to be not just some fabricated data for sure at the center of it, but also protocols known not to work that they keep reporting, keep using, putting all the research through one bottleneck in the lab that is a guy that's been there forever, and no one quite understands how the information that comes into that person turns into the paper, and maintaining that even when questions about replicability are coming in from outside. So, I think that institutions control the salaries. They're providing infrastructure where data is saved or should be saved. They ultimately have the ability to either document the data and have the data shared and available, to go in and make someone work with someone else. I think that when people get super frustrated, like at Bell Labs, it's because they want their institution they believe in their institution and they know it has the capability to check this stuff, and the checks there weren't happening. And the same is true at other institutions. I understand it's all organized by PI group, and there's reasons that funding agencies are doing that. But institutions then who are hosting all these PI groups, if they are then like, oh no, sorry, we can't share our data, or we don't keep track of data. Somebody comes from the outside and asks for data, or so another group in the same place asks for data and it's not available. And instead there's press releases going out and there's myth making about what a great institution we are, and how it's not surprising that our people are doing so much better than everyone else. So that's how I got it. Now I'm a whistleblower lawyer, and that's why, I end up suing or contemplating suing some of these entities, because an institution, just like a corporation, I've been involved in pharmaceutical litigation. So they ultimately taking some public money and doing something problematic. That's only for egregious cases, I hasten to say. And I know that lawyers are usually very persona non grata in the scientific community. That's for good reasons too. But I'd say most lawyers are working for the institutions, for the journals, for targets, subjects of misconduct, and they are trying to slow stuff down, keep stuff secret, issue libel threats and fraud threats. And, that's a whole pattern of activity. And many lawyers doing that are vastly better trained and more expert than I am in misconduct, and far better paid and better financed. So, this is where the legal brain power is. And you're not going to see any lawyers like that, and I might be wrong, please speak up if you're here, but joining this meeting and even talking about that type of work.
Okay, thank you. Appreciate your perspective. And I'm sure that a very large fraction of this audience has read your book. I found it very inspiring in a certain odd way. Okay, I want to get to Jessica Thomas. Sorry, I should have said I'm just doing these in alphabetical order, so you shouldn't take anything from the order here. You are maybe in the uncomfortable position that there's a lot of us find it very easy to just blame the journals, like, oh, the journals are creating bad incentives and that's creating bad behavior. So I think it's very important that we hear from someone who's actually working within sort of the journal system. So a question that I'm particularly interested to hear you comment on is, there's sort of this bias that some of us are railing against, that it's harder to publish a refutation of an incorrect claim at the same level of visibility at the original claim. Do you feel like that's a fair criticism? And if so, what can be done to increase the visibility of work that's refuting unreliable claims?
Okay. Yeah, so definitely I'm in the hot seat, but that's okay. So I want to learn from this group too. I mean, I think most editors of journals would feel comfortable saying that if a result was a big deal, a new result was a big deal, then refuting it, or the fact that it's not correct, would also be a big deal. I think that would be the spirit in which they approach it. I sort of took at face value the statement that it's harder to refute a result than it should be. And I think it would be really interesting to kind of get into some data around that, like how long is it really taking to really learn from that? But I think one of the reasons that it seems to take a really long time from the standpoint of somebody who's trying to refute a result, and I think here we might be talking about trying to refute a result that you think might be fraudulent, or where there was cherry picking of the data, more so than we're talking about like reporting a null result. I think part of what it is that when you feel like you're fighting for a truth, right, any delay seems like an incredible delay. So I think that would be part of it. From the standpoint of an editor, I think one of the things that makes this longer is that you're not dealing with the usual beast of peer review, where authors are coming in, they have a result to report, they're going in front of experts, and they're getting at it. There's just kind of like a well-oiled kind of process and seasoning around how that peer review works. But when it comes to refuting something, you've got a completely different situation, right? That tends to be rare, and you may not have seen as often, and every case is somewhat different. But you're
sorry, I think the intent of the question is like, even putting aside the issue of trying to get someone's paper retracted or putting a comment on a paper, say someone, publishes a paper in PRL or something that has some exciting result. And then another group comes along and said, we did exactly the same thing as that other group, and we didn't get the same result. So we did as best one could possibly do to try to get that same exciting result. And what we find is that it doesn't seem to exist. And I think a complaint is that it's very hard to publish that negative result, which would seem like evidence to the contrary of what the original group was claiming, separate from accusations of bad behavior.
Okay, all right, so that helps. So I think part of it is that and this comes back to the sociology of science, I I think, right? When you have a new result, right, something that no one has ever seen before, there's just kind of an intrinsic, I think, acceptance, right? Or we want to believe that you've discovered something, right? That's how science seems to move forward. And all you're fighting against is sort of the knowledge that, okay, nobody had seen this before, so you probably looked in the right place. But when you have a null result, I think it's more complicated, right? Because now it's just two things up against each other, the person who tried to repeat the measurement and the person who actually got it. So it's like you're having to, one person has to be right and the other person wrong. So I think it just adds to the complexity of trying to determine which one is like of equal importance. I think you asked though another part, which is how do we make null results or more visible? I mean, and when you had posed this question, I was thinking more of things like retractions, but I think that what I'm about to say would apply even to a null result. I think we don't talk about those stories very much. We don't write about them very much. And again, it's because we think, okay, well, maybe that's boring, right? It's not something new. But I think if we could make more of a narrative around what goes into actually proving something wrong, that there's a story there too, in actually how difficult it is to take something that's been discovered and then to think of a way that you need to maybe extend the analysis or do the experiment in a more thorough way. If we could find more of the narrative around that, I think people would start to talk about it more. And as journals, we could think of ways to bring that forward more.
I think this is a good point to allow the panelists to ask questions to each other, and then I'll start taking questions from the audience.
I just wanted to say something right in response to what Jessica just said, which is just generally when I was working as a science reporter, reporting in the scientific community, people would put emphasis in their interviews on being the first to discover something or having invented something, having realized something before other people. Even when I started reporting the Schoen book, some people like to say they realized it was fraud before other people. I myself framed it that way. I spent a lot of time asking people, when did you first realize, or who do you think the first person was who realized? But when I got to this chapter about people trying to reproduce, I realized this framing was wrong. There was nobody saying, I was the first person to fail to reproduce trans results, right? Oh, within a week of his laser being in nature, I had already failed to reproduce it. That's not the way it really works. If you want to close the book on a claim as opposed to open the discussion, there's no real ego in these groups, or there isn't room for ego in the same way. And there isn't room really for press releases about, we tried really hard and discovered, that something is hopeless. So that's my thought about what you were saying. And I don't have a solution, and I'm not a journal editor, you are. So I guess the journals maybe will come up with some way to write about this or frame it or make it interesting.
So I think that's exactly what I'm getting at, is that there has to be some way of celebrating the hard work that goes into figuring out where the problem was. You're right, that would require more work from editors and more sort of sleuthing, but certainly the stories that we've heard earlier today, they're fascinating, right? Just the process of trying to figure out what went wrong. Now, of course, those are more, that's why I make a distinction between like refuting something because there was fraud and refuting something because you tried the experiment again and it didn't work. And I think it's true that the first kind tends to get the more, I guess, high profile story because there's more of the human drama in it. But I think if we could look for ways to find a fascinating scientific story, the detective story of figuring out that, hey, this experiment needed to be done in this way to refute that earlier claim. I think that's where you could start to bring more attention to this really hard work that goes into continuing the science process and figuring out what went wrong in the first place.
That's not how you get funding. That's the problem. You don't get funding by showing somebody else is wrong. You get funding by claiming yourself that you have something new and the first in the world and everything. And so we don't really have time to do all this follow-up work. We're doing it. But
I think, if I look at the Schoen stuff, I think a lot of people weren't trying to reproduce Schoen's result. The natural thing is to assume he got it right, and then you want to build on it, right? And you can get funding for building on the result, but the first part of building on that result is you've kind of got to do what he did and then a little bit more. And then, you got funding for doing the little bit more thing, and then you suddenly find out it just didn't work. And that's sort of at the point that you realize something went wrong. And at that point, which is usually, a year or two later after the actual publication, that's about when you're ready to maybe make some definitive comment, which is often, unfortunately, outside the time window for some of the high-profile journals to actually write a comment. But it would be really great if there was a mechanism, sort of like, I think, PubPeer, but, attached to the journal so that you didn't miss it, that people could comment and say, hey, we're trying to do this and we're stuck. That might not be the end of the thing, but at least it's an early warning sign that maybe there's a problem.
That's an interesting suggestion. And of course, that opens another psychological can of worms. If I'm a famous scientist, influential, say at Harvard or Princeton, and you are assistant professor in some mediocre college, how likely you would be to make me your enemy by sort of attacking you unofficially? Publishing a paper which comes to referee and so on, that's a bit different. But just a blog, we're getting too close to like internet flame wars this way. And also there is no protection from, unfortunately, there is a number of crackpots around as well. But I'd like to ask a question to our editorial community, so to speak, Jessica and other editors present here. What do you think about the proposal that I sounded here and he received several positive raised thumbs about making that a stated principle, that a paper which can pass the referee process and disprove or debunk a claim that was published in your journal automatically passes the muster of being sufficiently important for publication. So if that is, say, Nature Communications published a paper, I can prove that this paper was wrong or even manipulated. I submit that claim. If it goes to the referee, if it's referee decides that I'm right, that's there's no burden of proof on my side to prove that this paper is sufficiently important and interesting. What do you think about this principle to be explicitly stated and implemented?
I don't know if that question was directed at me. There is another editor in this chat who might want to speak up. But
no, there's more than one. I think there's Ed and there are a couple of other people.
Yeah, if there's anyone else who's an editor and would like to reply, raise your hand and I'll unmute you after Jessica's done.
One thing I was going to say is that I think one of the issues is that it's often not very clean. When a result comes in and it refutes the first thing, what may often happen is chipping away at a result with many different groups, or maybe one group trying many things. And I think that can often get in the way of sort of the simplicity of just saying that's wrong, right? Because a signal is very clean, right? A new signal that no one's ever seen, and so that gets published. But the non-signal tends to not be as clean, not as obvious.
I think that's the matter for referees. Just the same way as referees decide on the original paper, the referee should decide whether a counterclaim is sufficiently demonstrated. If they disagree and say that it's questionable, that's a different story. But if they do agree, then the question is whether this negative result is sufficiently important. If the original paper was published in PRL, would you think that the paper which just proved and the referee agreed that the original paper was wrong can be published in PRL as well? Or it's just not that interesting? Okay, fine, that's not there. So
I think it could be I think it could be as interesting. I could get in trouble for saying that, but I would think often it would be as interesting if it's really clean and obvious. But I think the other editors should speak up too.
Okay, let me pass the microphone here to Yanko Milev, who's a editor at Physical Review BE.
Hi, thank you. Well, I've been for 13 years with PRL, so I have some experience, 20 years in total. The point is here, Igor, you know better than to ask this question to editors from Physical Review. You know, actually, that we pay much more attention to such cases, difficult cases, than to any other case. And you're asking it rhetorically, but if we dig into our database, which we won't do right now, since we always think about things and we look what we're doing very carefully, there will be cases where actually we acted precisely in the way you want us to. And like you say, you kind of slipped the word immediately when it almost seemed like, oh, anyone sends us something and we immediately critical and we immediately publish it. But then I understand you actually mean it has to pass the master peer review. And again, I'm telling you, such papers are really very carefully considered. I'm speaking here, not off the top of my head, which ain't here anyway, but out of my 20 years experience. So do I want to paint us as innocent? No, because the question is not if we are innocent. We are into the business of publishing. And so I can only tell you that we are doing things much more carefully than what you see or the people participating in this are saying. So, okay, I guess Stephen has to say something. He's the peer review editor.
Just one word, Yonko. I think that PRB is actually the least culpable journal, but it also is not necessarily because you guys are great, you are great anyway, but also because the problem gets exponentially and increasingly more severe when the reputation, the impact factor, selectivity of journal increases. So as good as PRB is, it's not PRL or PRX, definitely not Nature or Science. There, the problem becomes much more important.
Okay, sorry, just very briefly, I promised that I would stop this recording at 3. So as soon as I'm going to let Stephen Nagler talk briefly, and then I'll let Eugenie Reich, and then I'm going to stop the recording and the discussion can continue.
So I'm a new editor without that much experience in it. So take these with a grain of salt. But Igor, I definitely agree that these papers should be published. But I don't know that the problem is exactly with editors as much as it is with the community. And I will relay a specific experience that happened to me many years ago. Somebody published a paper in PRL, which made a claim that seemed a bit dubious to us on a certain material. And we had obtained experimental evidence that showed the claim had to be incorrect. The reviewer came back and wrote a review that said, obviously, this paper is right. The original PRL was clearly wrong. However, that paper was obviously wrong, and there's no justification for publishing a PRL on this paper, which was clearly right from the beginning. And the paper was published, I think, in PRB, which was fine. The data got out there. But after it was published, we noted that that incorrect PRL was still cited several times. Right? But this is a matter of, somehow the referees, the community has to step up and sort of accept that these papers should be published maybe in the same journal.
Yeah, absolutely.
This is perhaps a bit a different issue. I mean, journal like VSF get so many submissions that it's very hard to make sure they all get the proper referees.
Mm-hmm. It's a problem, clearly, yeah.
I think Steve has an excellent point, and that's my experience as well, that I had referees in similar situations which were clearly competent and analyzed and dissected my rebuttal paper and say, yes, you are right, the original paper was wrong, but that's not the reason to publish it in this high-profile journal. I think that's the point where the editor should step in. They got the information they needed, that the counterclaim is correct and the paper was debunked. Then they make decision regardless of what the referee said after that.
Okay, I'm going to let Eugenie Reich speak, and then I'm going to stop the recording. Go ahead, Eugenie.
It's okay. My thought went away. I'm sorry.
Okay, all right. The recording is now stopping. Okay, so this is the extent of what's going to appear on the YouTube channel of the Virtual Science Forum, and we can continue the discussion for probably another 55 minutes if people want. If the panelists or speakers have to go, that's fine too. This is all after school activities. Okay, yeah, panelists, you don't have to raise your hand. Jessica Thomas, if you'd like to go, please do.